And recording in progress. Okay. So I will try not to make it that long. I think it was supposed to take us. I think it's Ellie, I'm just going to mute you. Boom. It's not going to take us that long. And I would like to also, if you have some exam questions that you would like to discuss, please prepare them, and we will just go over them when we finish. Okay. Or if you have exam questions that relate to a topic that we've just gone through, that we went over the material. Okay. Let's just solve them immediately after. That would be the best. The history part is definitely not important for the exam, just for you. Okay. All of this part definitely not important for the exam. Okay, of course you can see because my screen is huge. Can you see my screen right now? Like what we're looking at?
Yes, we can.
Perfect. Okay. Okay. So let's see where we begin. Machine learning basics. Okay. In previous exams, we've been discussing regression stuff, which I find the thing that I find most important for you guys to understand is the difference between the two kinds of regressions that we do. We have linear regression, and we have what is the difference? If someone can answer to in the chat, what is the difference between linear regression and logistic regression? As I said, I will not answer the question about backpropagation in RNN. Okay, Sabi and Koenig had the best answer so far. Linear is continuous problem. Okay, so basically we could use one neuron at the end that has only one value that changes along the time. For example, we saw it when we did semantics, when we did in autoencoders, when we reconstructed, we used L2 for the linear for the linear regression, or not linear, but for regression. And logistic regression is a discrete problem. Okay, so we have threshold, and we have bids, and we have, for example, for logistic regression that we have. Do we talk about it here? I'm not sure. Let's see, maximum likelihood. Yes. So we have basically two classes, and this is expanded when we work on multiple classes. Okay, if we have 1,000 classes, as we have 10 classes in CIFAR or in MNIST, etc., etc. So logistic regression is just the basic, yeah, and we expanded it to the most generalized case when we have more cases, when we have more labels to work with. Okay, but that's like what Fabian said. That would be for me the best answer. Of course, many other answers could be accepted, you know, because we just want you to understand that to see that you understand. But for example, linear regression has a closed form solution. Right? So we don't actually need to do deep learning to solve it. But most problems that we deal with, for example, classification, or for example, the key points that we saw in exercise 9, or reconstruction in autoencoder, these are not linear functions. Okay, so we cannot really solve them with just linear regression. But if we have a linear problem, okay, for example, just we have some data and it's kind of linear, we could plot it and we see it's linearly, and we want to find a model. Linear regression has a closed form solution, meaning it is much faster for us to find a solution. We just need to calculate it once. We don't need to do this iterative thing that we do in deep learning, right? We don't need to approximate the answer. Okay. So in previous exam, we saw that, for example, I think it's summer semester 2021, we saw that you guys need to understand those concepts of log likelihood and how to derive from that, for example, the BCE formula. Okay, and why does it work? Why do we have a log, right? Why do we use a log? I find it as a great exam question. Why do we use it like that? Because then you understand the math behind it. We don't have a lot of math in this course, but when we do, it's good. It's super important to understand it. Okay. So for example, why do we have a log? Why do we have a minus? Why do we use the? That was one of the most common questions. Why do we use a minus in for example, here in the MCE? Okay. Why do we have the minus here? So who can answer? Well, we use log to have a opportunity to move from sum to multiplication. Very good, Roy. And why do we have the minus here? Make it a minimization problem. Very good, because log gives us, because what we do, we use the sigmoid for BCE and the softmax for MCE, and we push our logits. What are logits? Logits are the scores of the network before we move them to the loss function. And we push them between 0 and 1, and log of a number in this area is always negative. Perfect. Yes. Very good, guys. The log, Agatha also mentioned that we can use it mathematically in a because it's not decreasing function, so it preserves the bin max. This is also a very important characteristic of log, and which is also a great exam question. Why can't we use the log? Okay, because it does not, because the optimals of our function stay the same. If we change that, well, we do change the problem that we try to solve. Okay, why do we have this sum here? What is important? What is interesting about the MCE? Okay, and what does it represent? What do we iterate over? Yeah, it's the output dimension. Okay, but so example, what is this? What numbers could it take? This variable, the ground truth, 0 and 1. Very good. So what I was looking for is the term one hot encoding vector. Okay. For me, for when I saw it in the first time in the lectures, they did not use it like this. I wrote it like that for you to understand that we use the one hot encoder, because if we have 10 classes and the actual label of an image is 7, right? It's a plane, and planes are 7s. If we put it a 7, that doesn't make any sense, right? So it's important to understand that we go over the one hot encoding vector that each image gets at the end. Okay. What else was important for me in this thing? Yes. Okay. So that's for it. For L2, we have it here. I think I'll just jump and I'll come back. Okay. For L2 and L1, this is something that we saw, and we also saw it in many exam questions. Okay. A lot of questions. For example, let me see if I can find it. The one with the half. The ones. Okay. I know. Okay. 2 exams. Let me open this. And I need the mock exam, so let's just go here. And was it this one? Yes, the mock exam. Oh. You said disease, and I don't understand what you mean. Okay, there was a question. If we're talking about loss functions.
Yeah, because I mean, because in one hot encoding, we assume that only one, like this is a classification problem, so only one class is correct. There's gonna be only one, right?
Mm-hmm.
But it is possible that we have like a problem in which we don't only have one class that is correct, but could be more than one. So for example, you have like an image of a person and you have to say, oh, does this person has this disease? That like is an example. Or is there a cat or a dog in the picture and we have like both? Can we still use then this loss or?
Okay, but this is different problems. We don't solve them as this classification. For example, if we want to recognize in an image both dog and cat, we don't just want to give a label to the image, which was what we did at the beginning. We want to do semantic segmentation and to each pixel to classify to what it belongs.
Okay.
Okay. So we will segment each pixel, and then we can see that there is actually a dog. And then we could collect it and see, oh, we actually have pixels here from a dog, and we have pixels from a cat, and we have pixels from sky. So we could say that there are a lot of stuff in this image. Okay. But if we just want to classify an image to some label, it's going to be 1. Now, the next thing that I want to talk about, in the mock exam, we had this question, and you needed to do backpropagation through this computational graph. And I hope all of you guys went through this and understand how it's done. Oh. Can you see me? Am I frozen?
You were frozen, Dan, for a couple of seconds.
Yeah, it's because for some reason the Zoom takes so much resources, and my 16 GB RAM computer cannot handle that. I'm so sorry for that. Please stop me. Please write it when it happens, so I know to stop. Okay. Perfect. Okay, so I hope all of you have went through this question and understand how to go through backpropagation and what do we expect here when we have a mission and we have, for example, with two neurons, it could be either at the end, it could be either MCE, this could also be regression. I think here we use the L2 loss, the MC. Okay, MSE. First of all, we don't know if there's going to be a backpropagation in the exam, but I had a saying to say that if we are going to do anything like that, please just don't do it like RNNs, because it's just too much for the exam. Okay, so what I want to, one of the questions that we're talking about here is if, okay, we always said that we divide the loss, as we saw here, with n, with the number of images in the batch that we put in the we feed into the network, right? Okay, so why do we cut in half here? Okay, so this is important for the regression problems, like we did when we did in autoencoders, and we reconstructed the image, and we went for each pixel, and we compared it with the corresponding pixel in the input. We want to divide by the number of times that we do the regression. So if we have a linear regression and they do not correspond to each other, for example, they do not represent the different numbers, and then we just pick one of them, right? So what we did here is to pick this is okay. What we did here is to pick only one out of the one hot encoding. So this basically this sum is redundant. We don't need that because we just pick the relevant one. So this is always going to be 1. So this one basically it's also redundant. But for regression, we count all of them. So this is also important to divide by the numbers of operations that we do in this inner sum. I just don't want you to waste time to do backpropagation on RNNs, because this is not going to be in the exam. I don't know if a backpropagation question is going to be, but everything else could be. RNN I asked specifically needs to have. But I figured, I saw the previous exam. You saw how many questions you guys had about this. It's just waste of time. Yes, but RNNs are, and the topics that we cover there, like there are a lot of stuff that is important in RNN because it's a basic for all the consecutive things, like for example, NLP, right? But for example, I'm using in one of the projects right now, transformers, which is super important to understand why. And transform and RNNs and LSTMs were more important, are important to understand the basics to transformers, and why we did transform and how it was developed. So that is important. This is the very basics of this topic. So that's important. Backpropagation also it's important to understand. I don't think that we will ask you to do that in the exam. Because I think it's a waste of time, of your time. Okay, where were we? Okay, so is this? I didn't understand attention transformers. So if there's time, you could expand again. 11. Yes. Okay, but isn't the 1 over n on any other in front of the loss irrelevant in the end? Like we can just, okay, so this is important. Yes, you could, not for every, but not for every problem. For example, if you use the Gaussian-Newton method, we don't use a learning rate, so it doesn't matter. And I do not want to go and change the learning rate every time I change something in the input. So it's good to have two different hacker parameters that we do not correlate with each other. Okay, so like this is the convention to do, and this is how we expect you to do it. Like, of course, you can change stuff, and mathematically things could work otherwise. But there is a one-way convention to do it because I think it's just it's more easier to do. So I would just rather if you stick to that. Okay, but it's a good thing that you guys think about it. Okay. So why? Okay, in MMC is in a nutshell, because we for the question of Eric, why do we use this? The half here is because we have two output neurons here that we use both of them for the result, for the loss function. In the loss function of L2 that we use in the MSE, and like I'm sorry, I'm going up. We basically use both of them. In contrast to what we did in for example, in MCE, in multi-cross entropy classification, we use only one of the neurons. We pick one of them, right? So here, if it was an MCE, not MSE, and it's important to notice the difference, we would have just picked one of them for the loss. So we basically don't need to divide by anything. Okay. But if we had two outputs neurons and samples in batch, would it be? Yes. Yes, that's what it would be. But I think for simplicity, it's good that you noticed that. For simplicity, I think that most of the questions have only one image going through them. So Leonardo, pay attention. You said 4 because you thought there are 4 neurons at the end. The 4, we have only, it would be only 2 because only 2 are taken into consideration, and the 1 over n would be the how many images or how many inputs we pushed in one time, we fed in one time into the network. This is important. Okay, so here we use 2. Very good. Okay, let's unless there are no more questions. Oh, so if we have 5 output neurons, it's just 1 over 5. If we're using them all, if we had the auto, let's just go quickly. I'm at page 14. Okay, if we go to autoencoder, where is the autoencoder? Did it just disappear? Oh no, here it is. Okay, for example, do you see this? You will also divide by the number of neurons here because they are all taken into consideration while we do that. Okay. Let's go back to 14. Boom. I think there is a better part where we talk about gradient descent in this format, so we will talk about it in a sec. Okay, so this is something I always ask you guys. What is the difference between gradient descent and stochastic gradient descent? Try to answer. You can answer for yourself, but I would also rather if you could answer. Eric, not true. Again, not in a vague answer. GD, update every epoch. SG, iteratively update the gradient. Okay, iteratively, so it means every iteration, because epochs are also iterative, so it's important to understand we do it every iteration or every batch. Okay, so for Agatha, for your answer. No, I think who did that? Fabian, I think. Yeah, gradient descent update every epoch, stochastic gradient update iteration. Yes. Okay. So I saw as I saw from the answers here, understand that we can do gradient descent also with batches. Okay, where we just accumulate the loss and we do the optimizer step at the end of the epoch. Okay, there are two stages. We do back propagation and we do optimizer step, and they're not together. And I saw some confusion on campuswire. If I would use SGD with batch size n, I would have done SGD. Yes, it's like how do you call that? Not redundant case, but a degenerate case. You know, but you could do also gradient descent in this. Okay, now the next question would be, what are the advantages of stochastic gradient descent above gradient descent? Some of you have already tried to answer that. Wait, okay. Just let me open the chat, and I'll go one by one and try to see. I would, yes, but not such as anymore. 7 points escape. Okay, so guys, this is important. For the exam, you are required to put key points or the keywords in your question, in your answers, because we have 1,500 students registered to the exam, and we are 8 tutors. So what we're going to do is we're going to go over your answers, and specifically because of handwriting, and most of us are men, unfortunately, so we cannot write. We are just animals. And we cannot have, so we basically want to see the keywords. We're going to look for that. So if you say saddle points escape, why do we escape the saddle points? Okay, but why? What does stochastic gradient descent introduce into the network, into the optimization problem? Noise. So noise is a very important keyword that I would expect to see. Just a sec, I'm going one by one, so just a sec. Running time. Okay, Roy said running time, but why running time is what do you mean by running time? You're correct. Okay, but like why? What is it? I mean, the convergence time would be different. Eventually, we're going on the same number of the points, right? So I would rather have full answers. So let's think how we could do that, because it's either you guys open your mics and talk, or you write your full answers in the chat. Because I would rather, actually, this is great practice. I want you to practice to write your full answers. Like if the answers you could see in the exams, we require you 1 sentence for a question, but it needs to be accurate. Okay, so if you say running time for stochastic gradient descent, it's because gradient descent does the update for the weights at the end of the epoch. Okay, and it's bounded by the learning rate. So no matter if it's more accurate towards, and the stochastic gradient descent does more zigzag. Yeah, if I annotate, where is that? Where is my bar? Oh, it's here it is. Annotate. Let's just go up a little bit. Okay, and let's see. Annotate. I know that you guys, some of you have already answered that. So this is like the loss curve. And if we start here, and while gradient descent will do this, right? And gradient descent is more likely to do this. Think if this is a step of stochastic and this is a step of gradient, like let's say they are the same size, right? This will happen more frequently. So basically we converge much faster. If you do gradient descent, if you wait to do it at every epoch, you will have to wait until the end of humanity for your network to converge. So basically this is what we mean by runtime. Okay, let's continue. Agatha said, I have a question about batch size. I know small one is from regularization and big one is usually limited by GPU power, but why would we eventually want a bigger batch? Well, a bigger batch, it depends. What do you mean by bigger batch? A bigger batch could be 16, and it could be 512. A bigger batch, we would have loved that. We would love to do batches because of this noise. We want this bit regularization, so we don't want it to be too big. Okay, but we don't want it to be too small. Too small could be does not represent the statistical properties of the data set. So if you change the shared weights by the gradients that were lent on a small batch, you most likely you did not take into consideration a lot of stuff that are in the data set. So you're going to change, for example, the shared weights. Also, frogs, the images of frogs used by derivatives that were taken on horses and cats. Okay, so again, we want to do that, and also for batch normalization, it also introduces too much noise, but we'll get there. Okay. So faster updates, I2D escape saddle points because we have more noise. It needs to be smaller learning rates because we don't have momentum. Fabian, very good. Running time, less updates needed. I guess most of us don't need full. Yeah, okay, we saw that. Okay, so it would be okay to write keywords only without adding unnecessary fieldwords. If you say, for example, it reduces noises, and then it allows us to escape saddle points, that's a full answer for me. Okay, like I'd rather not to read a story. I'd rather to have 5 seconds of your answer, give you all the points, and continue on. Eventually, I have to grade it. Okay, so you need to think what Dan wants to hear. That you brought a beer. Okay. I guess most of us don't type for, we saw that. Should we also mention that noisy grads in SGD help escape local minima apart from saddle points? They will both work. We understand that you understand, because saddle points, you should know how to define saddle points, yeah? What is a saddle point? So yeah, for Suban, for your question. So it's faster because we have less epoch with SGD. Yes, we need less epochs with SGD. That's also a good answer. It is true to say that the gradient descent needs to use more memory and take more into compute. So if you take the entire data set in gradient descent and you try to push it into the network, yes. If you do batch gradient descent, not stochastic gradient descent, batch gradient descent, it does not require more memory. It is true to say, so it's faster because we have less epochs with faster. Okay, it is true to say the gradient descent. Okay, yeah. Sorry, momentum SGD. A smaller learning rate comparatively to Adam, but it's also smaller. That I don't understand. I already lost the context. So in one sentence, compact, why is SGD faster? Because it introduces noises and allows us, and we update much more frequently, for example. Okay, that for me also works as an answer. Let's remove all the notations here. Clear. SGD is less likely to get stuck there because it has noise. It does not go immediately to 0. 0 is a theoretical point where all the data set, like it's a 0 of the gradient for the entire data set. But if we use just part of it, we don't go there. Yes, it's also regularization. How does noise make it faster? It does not make it faster. The idea that we use every batch, not every epoch, makes it faster, because our optimizer steps are bounded by the learning rate. This is the length of the vector that we take. Okay, if this is the minima and we are here, this is stochastic gradient descent and this is gradient descent, for example. But this is done much more frequently. This will take much more time to compute. No, the noise just allows us actually not to converge to saddle points, to actually go to the minimum. Okay, another question that will appear in different exams. Why do we? Okay, usually we will converge to a local minimum. Why don't we actually care? Very good. Okay, yeah, you guys really overfit over the material, and I like it. all answers would have been accepted. Very good. Okay, let's continue. Actually, those who will see the recording, okay, the answers were, because they will not see the chat. Local minima is good enough. And I think Oliver has said, because NNs, neural networks, are over-parameterized. Okay, gradient descent, we've been here. Let's see, I need some context now. Okay, gradient descent. Okay, when we talk about optimizations and backpropagation, first, I wanted you to solve all the problems, and you have to do it fast, of computational graphs when we see in the exams. Okay, you need to understand how gradients flow and what do we for example, what values will go through sigmoid, or how do they look after they go through sigmoid, and how do they look after they go through a ReLU? Okay, this is important for the magnitude, for their sign, and how it will it, for example, if we use a tan H, do we expect it to go into saturation? Do we expect it to be in the great area? For example, what would help us in tan H to stay in the proper area where the derivative is actually makes any sense, right? For example, what could help us with tan H to do that? I know it's random, out of the blue. Very good, savior initialization. How it is called for ReLU? K-mean initialization.
Is that K-mean?
Yes, K-mean. Gradient clipping. Okay, that's actually did you touch this in this lecture? Interesting. Okay, so that's also good. That's also a great option. I don't think that most of us talked about it, so I will not discuss it here. Those of you will go to the advanced deep learning. Okay, yeah. Also, batch norms helps us put them in the proper place. That's also a good answer. Okay. We talked about gradient. Okay. I wanted to, in this part, I wanted to know how to derive stuff. Okay. I wanted to understand how to derive like the loss functions, the BCE, the MC, the derivative of L2. L1 is a bit tricky, so no. I wanted to understand how to derive an affine layer. That's what we did. To derive a ReLU, to derive a sigmoid. Okay, all of these are important.
Sorry, what do you mean by deriving a ReLU? I mean, the formula is clear, but do you mean like in the context of some architecture, or what do you mean by that?
I mean in the context that you get, you do backpropagation, and you need to understand what's going out of the ReLU back, like to the. If we had here a ReLU, how does it go back to the next stage? To the next stage, okay. I think it was actually in the revision of MCE we did in exercise 2, which is the mathematical background. L1, I do not require you to know. L2 is basically to derive. That I would expect you to know, because that's like the easiest one to do. It's just a proper derivation of x to the power of 2. The MC has to stay, like you did it, and I really think you did it in exercise 2, and you had 2 stages when we derive, when we have the right one, and when it's not the right because the right label, okay, ground truth, okay. For example, here L2 loss. So how to derive that according to y hat. Also important for you to understand how to derive I want you to go over the Stanford paper that we did at the beginning. I will talk about the weight decay. I want you to go over the Stanford paper that we did in the beginning and understand the concept. I still see which is okay. Yeah, no hard feeling here. But I still see questions about that in CampusWire because people try to solve the questions from Stanford, which I still regret that we gave it to you, but still, and don't understand why things do look like they look. And if you do understand the concept that we went over in this session that we did, you will understand how to solve it. Yeah. Which paper exactly? Sorry. Okay. If you go to CampusWire and you go hint, sorry, CampusWire works really slow, but this is what you pay for a free platform. You can go to derivative session number 2, and then here you could find either the YouTube video that we did, that I talk about what we did here, and you could find the PDF here, and you will see the stages that we did, how to derive matrices in a null network, because it's not obvious, it's not trivial, and it's definitely not what you think it's going to be. Okay, I would like to move on. So you wouldn't recommend using the old Stanford exam? I would definitely, but they could be really hard and not really what you've seen so far. And so a lot of questions, by the way, do not relate to what we do. Like I've looked at them, and a lot of questions are just out of the scope of what we did in our lecture. Okay. So there are good questions there. A lot of the multiple choice in Stanford are really good. Some of them they don't use the same notations that we do, and they could be confusing for you. I would take also in CampusWire, I did it here. I shared with you guys with derivatives reading materials, the original article from Stanford, and they have an example there. You try to solve it yourself. The question is, okay, but when we at Stanford, we define X with rows are samples and columns are figures. But does the derivative also hold if it's defined as a column samples? Yes, it works the exact same thing. You just need to understand that now it's transposed and solve it as it was transposed. Like if we have XW, as we know, for example, we in a affine layer that we define Y equals XW plus B, right? This is how we defined it. And the derivatives was according to this. And if we do it Y equals WX plus B, this is exactly the same, but we derive it differently. Like the derivative here of the X with corresponding to an upstream gradient that comes into this layer, yeah, of X is going to be D out, which is the upstream gradient. This is how we called it, multiplied by W transpose. If we do it here, the derivative of X is going to be D out of X, sorry, it's going to be W transpose D out. Okay, this is the only difference that I would require you to understand. Why is this the derivative? Go do the other session. It's 1 hour and a half. Have fun. Agatha is asking, okay, also usually after a fine layer, we get activation function. I'm still struggling how to multiply the gradient from okay, but that's what you need to remember. That's what you need to remember. If you had a ReLU for you is it's the abstraction that we do. So if we have a affine layer that goes into a ReLU afterwards and then goes to something else, all that happens here, we assume it was already calculated, and it's basically what we call D out. The ReLU had the exact same thing. When we went to ReLU, we had some D out of its own from here that came to it from here. So that's, I think it's super important to understand what you did so for everyone to follow what we're talking about, it was, do you remember what exam was that from Stanford? I think it was this one. clear drawings. For example, in here, a question that I would not require to understand how to solve, and people tried, just really out of our scope. I think is this one, right? Here, basically, when you see these, okay, this is the D out that was calculated. So each one of them is calculated in its own way, and you just you plug it in after you've calculated this already. You just put it as a D out. You need to calculate the out or the upstream gradient, but by itself, okay? They did not show any stage of how to calculate it, but if you follow each one of the layers here by the Stanford mechanism that we showed at the beginning of the lecture, you will know how to solve this. This is also a great practice, but it's hard, okay? But what can you do? Okay, I would like to continue because we still have a lot to talk about. Okay, so for Eric's question, let's talk about regularization. Okay, at which case are we going to use regularization? And what keyword do we really like to hear here? Overfitting. Great. What will we see in a graph when we do overfitting? The answers, by the way, are overfitting. Yeah, val increase, train goes down, validation loss higher than training. Okay. Agatha, that's almost, because it's also true for a network that trains well. The generalization gap, very good, guys. The generalization gap is getting bigger and bigger. Okay, that's what we'll see. What we overfit. This is why we use. Okay, for that. We use regularization, and regularization are a family of techniques. For example, the weight decay that we're going to discuss now, but it could be also data augmentation. It could be dropout. It could be even not trivial things like making the data set, the training set, bigger is also a regularization technique, because it will have to generalize better for all of the data set. Okay, but it will, of course, the error will be higher because we have much more data set to generalize out over. Smaller batch size would also count. No, that's not true, because it does not make the gap. It will just make your training set go like zigzags. I would not say this is regularization. It also introduces noise. Yeah. But you could also really easily overfit with a small batch size. It depends on how big your training set is. Okay, so let's talk about this term, which is not trivial, but you should definitely know that. Okay, so basically what we try to do is to say, okay, we have the loss functions. We want to introduce some noise into the network, because what is this? What we do here, yeah, is to just put some numbers into the loss function. But what happens in the derivative, it will for each one of the weights, we will try to push it to 0. Why? Because we want this. Eventually, all that a network does, a neural network does, is to minimize this term. It does not care for anything else. It cares to minimize this term, to push it to 0. So in order to push this to 0, it will try to push all the weights to 0, right? It will try to resist this term that actually does a good job, okay? Because we will try to put some obstacles in the way. That's the intuitive way to think of weight decay, okay? Where do we put that? We put that in every layer, okay? We saw like when we saw, you guys did not have to implement that. We did it for you in, I think, exercise 3. But for example, in the Stanford version of this exercise, that you had to do it yourself, and you actually saw that you had to do a regularization term at every step. You have you take the weights. It doesn't matter if you do it here, right? If you put it at the end, as long as you put all the weights from the network here, or you do it at every layer, okay? But eventually, this one needs to be like all the weights of the input of the network needs to be pushed with this regularization term. Okay, this is understood. Why do we use lambda? Okay, because we don't want it to. This one is really, really hard term. Like if we push it here, we will not learn at all. Okay, like if so, it means that if lambda is too high, so we don't penalize this too much. Basically, we will not learn. What we will see in the lecture, in the graph, we will just see that both validation and training will just converge on a very high error rate. Agatha is asking, but we calculate loss only once. How can we do it every layer? We will have to go into the implementation set. For simplicity, just say we take all the weights of the network and we push them here. Okay. Lambda here is not the learning rate. No. Oh, these are great questions. So it was asked if the lambda here is a learning rate. It is not. It is the weight decay hyperparameter. Okay, so what I want to emphasize here, that this one needs to be small, not too small, but small. Because if it's too small, we don't do any regularization. And it's like every hyperparameter. For that, we have the hyperparametric phase that we will go, I will think we'll discuss it later. Yeah, we'll discuss it in lecture 6, right? And then we'll discuss all the things that we can do with it. Okay. What I do want you to understand, I don't think actually that we have it here, or we do. Let's see if we do.
Sorry, can I ask a tiny question regarding weight decay?
Yes, of course.
Okay, so what I read was that once you add it to the update rule of gradient descent, it's called weight decay, and if you add the penalty term to the loss, then it's L2 regularization. Is that correct, or is that somehow wrong?
Oh, I don't know, because we never made this distinction. I would like to read that. Like it could be, because I hear both of them. For me, I decided to go with weight decay as this, just to put it here at the loss, because L2 and for me they're synonyms. Okay.
The update rule and the loss are synonyms, or you mean L2 reg and weight decay are synonyms?
Like the update rule, but you have to take in the update rule you use that, right? But in the update rule you have to you take the derivative of this. What I'm looking for now is, I don't think we have it here. Someone of you students have to put it here. The derivative of weight decay of the L2 regularization. I don't see it here. Which everyone will benefit from. But basically, we saw it in previous exams that you need to know the update step of the regularization, of the loss with the regularization. Okay, so for the relevant weights, how do we? This is why I say we do it every for each layer, because we basically, when we update with the corresponding weights, right? Although all of the other weights will be 0. But basically, you need to know how to derive this. You plug this in and then derive this, and we expected you in previous exams to see it in the formula. Okay. Agatha is asking for the update step with the regularization. If we use SGD, for example, do we also put learning rate in front of the reg term? Yes, because it's part of the loss. Where do I? The problem is that for this session, I don't have it here, so we cannot see it, but maybe if I can try to write it down for you. Okay, so we have, this is theta, okay, K plus, forgive me for my drawing skills. And we have theta K, right? We do learning rate. And we have the derivative of L according to the weights of weight K, okay? Plus the derivative, I'm just saying here derivatives, I might be wrong, okay? Don't take me on this, but the derivative of this term. Okay. This is this is lambda for all the confused people. This is lambda, okay? And we expect to see this term here. You could, of course, open it up, and there are many ways to write it down, but eventually it's all the same thing. Okay, this was important. Okay, this was important. I think that it's too vague from the lecture. Can we say, Engines asks, can we say that L2 loss pushes weights towards 0? Yes, definitely. Or with L2 loss, L2 loss? No, not the loss, not the loss. L2 regularization does. No, the thing about L2 that it penalizes more towards outliers. Okay, so we want to generalize even to the outliers, and L1 does not do that. Like it has much more robust to that. The L2 regularization pushes things towards 0 because we apply it immediately on the weights. I think we have this comparison of L2 and L1 in the future, and we will go over it. I think there was a question that came a lot of time on CampusWire. Which one of the following loss functions, L2 and L1, can actually theoretically reach the 0 loss, and the other one can't, and why is that? Who knows the answer? Theoretically, practically none of them. I think we could go CampusWire and find it, but there are too many posts here, so it would be fine to find it. Ah, here we go. Someone, okay, here. So Milena is right, because if I think that we can see it here, I actually had to post it, people could understand, but it takes some time in CampusWire. Basically, L2, it's defined, the derivative. That's what we asked if in theory. The derivative is defined for L2, and for L1 is does not define. Okay, so we can't get there. Here we could if we somehow wanted to, but because of the learning rate and because it's just steps towards the, we will go into infinity and we will never get to 0, real 0. We'll get something very close to 0. K is asking, so for the update step with regularization, we put LR, learning rate, before the loss gradient and before the reg parameter, yes, because the regularization is attached to the loss. Okay, this is why it's also a part of the loss. But if you write to me in the exam as I wrote here, I'm like, I'll have to do it again. Okay, sorry guys. Theta K. So this is circle is theta for now, and and this is ta. And if you do this is learning rate. This is the loss, and if you put the derivative of L of theta K plus the regularization, lambda regularization, okay? If you write this in the exam, you get all the points. If, of course, it's a question that is. For example, I had it in my exam when I did I2DL, and no one explained it to me like that, and then I didn't know how to. I saw it in one previous exam and thought, that's easy to do, and then I didn't know how to do it. Lost points. Okay, what would I like to discuss? Important stuff. Okay, so I think that we saw that. Okay, we did discuss that. It's only when we can go to the global minima. I guess we all saw the answer already, but okay, I will not ask that. But when it's strictly convex, when usually it's not strictly convex, this is why we usually go to local minima, but we said it's okay, it's good enough for the problems we try to solve, because in deep learning we do applied mathematics and we don't need really the global optima for that. It's when it's good enough for the autonomous car to drive, it's good enough. What else I would like to discuss here? I think we can go immediately to momentum, to optimizers. Okay, optimizers are also a very major topic that I would like to discuss. Agatha is asking, there was a discussion on Telegram, but SGD with the optimal learning rate will for sure convert to global minimum for context. Yes, okay, yes, but remember that this has to apply also. Okay, the question, I'm sorry, I have to repeat the question. If as we use SGD with optimal learning rate, will for convex problem, will it converge to the optimal minimum? Yes, but it will, but it has to follow this one. Which mechanism that we saw in the lecture does that? Allows us to actually answer that. Not weight decay. Learning rate decay, yes. And I think this is what you meant. I think you just confused them. But pay attention. Pay attention, that's not the same thing. Okay? Learning rate decay. Why, if we did not use learning rate decay, we would get stuck at some point. We just overshoot. Yeah, overshoot, by the way, another keyword that we really like to hear. Okay? For example, when we talk about momentum, yeah, and that's which is the next section. So we want to talk about overshooting and why. Okay, so basically, what is the point of using momentum? I want a full answer, guys, in the chat. I will go over all of them, so don't worry. So past saddle points, it's not a full answer. Damping oscillation and gradients is not the right answer. Agatha said something in Latin. To get faster to the minima by collecting previous gradients. That's already closer. For those of you who talked about saddle points and local minimas, I would like to see overshoot. I want to hear these keywords. Engine also said going faster in the direction where gradient is large and consistent. Yes, accumulating previous movements or previous steps is also a good answer. Okay, to overshoot or to avoid saddle points, to avoid local minimas. Okay, Tay had the best answer. Momentum speeds up movement along directions with strong improvement, loss decrease, and also helps the network to avoid local minima in one sentence. And that's a great answer. If the saddle point is gradient is 0, if not using momentum, the learning passes and stop on it. The momentum has to pass over it. Okay, that could also be accepted, but you need to remember that we're looking for you to say that it is accumulated. This is the mechanism, right? This is what we do. Now, pay attention to this accumulation thing. I know that in literature, we call this this is what momentum, right? But then we go to RMS prop, to this thing, and to Adam, and we have this thing, and we say also we have momentum. Now, in literature, this is what we say. So if you say that in the exam, we will forgive you and you'll get the points for that. Okay? But pay attention that it is not exactly like momentum. It is momentum when this is equal to the learning rate is equal to that. And if if this is 0.9 and this is 0.0001, because this is the learning rate we choose, it's not working the same way. It's not accumulating it's not accumulating the first moment, or here the second moment. It's not the same thing. But if you say that, we will accept that to avoid any of the questions. Okay, but it's good for you to understand this delicate difference. Okay, let's go to the next one. But it's good, guys. I really appreciate that the fact that you try to write your answers. the full answers. This is super important. Okay, I'd rather to give you the time and try. It doesn't have to be anything. You can do whatever you want. Basically, we want to take mostly, we take beta 0.9 to be able to take mostly what we saw in the past. Okay, this is just the usually, like, this is also a hyperparameter. You could change it. Like it does change actually when we have like small batch sizes, but that's out of scope. For you, 0.9 is good enough, and because we want to take the most of the previous steps and then to change it a little bit, to modify it with the current step. Okay, for this it's not the same thing. Okay, we want to take the momentum that we accelerated through from last steps, if we had a huge slope, yeah, but still bounded to some step. Step size, but we don't want to overshoot to any optimum. Okay, let's take, I think Nestrov was not in your material, right? People said that you did not see that in the lectures. I don't know, I did not go through them. So we will go immediately to RMS prop. Okay, what if I ask you, what is point, or what is the task or the goal of using RMS prop? What will you answer? There's not one like specific phrasing to that, but you need to understand. Javier gave just the best answer: dampens oscillations of high variance dimensions. Okay. Good. Okay. What advantage does it give us? That's actually quite not tricky, but it requires you to understand. What does it allow us to do? Yes, Milena has it right. We can use higher learning rates because we're going in the right direction. Which leads to faster convergence. Leonardo has it also right. We can increase learning rate because it's less likely to diverge. Very good. Just the jittering is dampened when you as gradient pointing into different directions. Advantage is high learning rate. Very good, Paul. I would also add, so converging faster, but it's good enough. Accumulating answer the variance in expressional weight decaying average fashion in order to dampen oscillation in high variance directions. That lets us to increase learning head. Engine also very good. Can we also use Halle? So momentum does not do this. So it's a bit more problematic. And if you do, hi Agatha, for your question, sorry, I need to repeat it. Can we also use higher learning rate with momentum? And momentum will remember that momentum with high momentum, you know, if it goes down the hill really quickly, yeah, if this is the function, no, this is horrible. Just a sec, maybe I can go here. Yes, here we go. Clear drawings. Okay, so this is the function, and we are here, right? And so with momentum, because this is a very nice slope, we will overshoot, but then the momentum will lose, and we'll go like this. If we use a higher learning rate, we will just shoot over even furthermore, and then this one will take even longer. So I will not say that is true. Mouse. Here, clear drawings. Okay. Very good, guys. Very good answers. I'm proud of you. Okay. Isaac says RMS prop helps us weight the more recent gradients updates more than oldest ones, which allows us to change. Okay, that's kind of vague because you can change the learning rate all the time, not only with RMS prop. And that's true. That's what this mechanism does, but that's not the point of using this here. Leonardo is asking, will RMS prop be slower when all gradients are already perfectly aligned? But then this division is not much, like does not do much. So I guess not. But then we come to Adam, okay, which just takes them both and combines them. It changes momentum a little bit, okay, as we could see here. It changes it. It's not the same. And we have a learning rate here that not like here in momentum. I want to emphasize it again. It's not the same as momentum. Are all S2D with momentum, RMS per Adam first order solvers? Okay, that's Emmanuel. That's a good question. And I would like to hold on that. Maybe before we even to move to Adam, or maybe we'll just do Adam first and then, okay? So basically we just add them both here. And we use them both in the final formula. And I would like to discuss also the idea of bias correction. Okay, so first, Manuel has asked, are all SUD with momentum, RMS Prox, and Adam first order solvers? Now we've seen so many different phrasing of those. This is why I also insisted for that to be, if we do anything about optimizers, so it will not be phrased like that because this is stupid. When we say first order, we could talk about derivatives. So basically Gauss-Newton is also second order, right? So why is this? But sometimes we talk about RMS prop and Adam as first order momentums. And what does that mean? So I would like to say that let's just not talk about what order they are. And I will say that Adam and RMS prop use the second moment. Okay, this is because there is no discussion about that. Moment is a known statistical phrasing or term, right? What is moment? First moment is the mean. Second moment is variance, and there is no doubt about that. This is what they do. So for here we use the variance. Here we use the mean. This is mean variance. Okay, for that, no question. But for to say first order stuff, it's just not relevant. No one uses it anyway, anywhere else, and it's not relevant for your exam. So, so basically, I won't let. If there are no other questions about that, like you could say that Gauss-Newton is second order mechanism because this is what we say of second order Taylor, like the second order of Taylor series, right? So we take the Hessian and all. So that, yes, but I would not put it here. That's just trying to be smartass and say, oh, first, second order. I know you've seen. That's why we're trying this semester to do it better, to train, you know, for the best exam ever. Okay. We're not going to ask you about first order of how they're called, okay? Like if it's first order momentum, no. If you see first order momentum or second order momentum somewhere, we mean first moment and second moment. That's why I wrote this. This is for you last semester because it was a huge discussion and no one understood what's going on, and so every semester it's the same thing. Okay, I would like to talk if there are, okay, yeah, I wanted to talk about Adam, about the bias correction. Can I say, Katerina asks, can I say the main feature pros of RMS prop is that it allows to make the updates that are not monotonically decreasing over time, so we can achieve bigger effective learning rate if we need so at the same point. Also, it does not use the keywords that we expect you, and so we will have to actually sit and think about what you read. For me, because I haven't read 1,000 exams before you, I could say, yeah, okay, that is acceptable. But please try to stick to the keywords that we learned. For example, in here we say damping the oscillations of high variance directions, and that's what I would love you to write in the exam if you are asked about RMS prop, because I just know that you understand what you. Of course, you can just memorize that, yeah. But that's what it does. Like the most accurate way to say it. Of course, it seems, Katerina, that you understand what you're talking about. if we take points off and you say that in the, if you say, okay, this is what I said, to take another look and in the review, and okay, yes, you'll get the points for that. Okay. But keywords will just save you the hassles of going to the review or saying not that good of a grade. When the grades come, I know the feeling. And I'm sorry in advance. You know, what can you do? So Newton method. Okay, Newton method. As we could see in previous exam, there was a question to define it, and this was this was the sentence that was required there in the solution. The second order Taylor series expansion. Okay, here you see second order, but that's true actually. And we try to, what are we trying to do in Newton method? Ah, thank you. Yeah, Daniel. Thank you for that. Yeah, losing context. Okay, so the bias correction. I'm sorry. We wanted to talk about that before. Bias correction. What's the point? Why do we do the bias correction? That's a question. Okay. Why do we do this step? And pay attention that here, yeah, this is because beta is a hyperparameter. It does not change, but this is an exponent. It's not an index anymore. So what does it mean bias towards zero? Do you understand what this means? Okay. So basically, they are biased towards M0 and V0, which are completely random. Okay, those are random, these are random, and therefore it's really biased towards where we start. And that helps us to, because of this mechanism that we really penalize the new gradient, that this is zero. Yeah, these are zero. So the progress towards the loss is very slow at the beginning. And when we do that, if you just multiply, like you take this one, yeah, and you do this, this one is gone bye-bye, and this one is gone bye-bye, and we are left with just the learning rate, okay? And then that's would mean we could take actually more meaningful steps towards the minima. But then we pay attention, again, this is an exponent and not, like, of course, it corresponds to the index of the layer, okay, but is an exponent. So this one is going to be, this is going to zero because beta is below one. So eventually this will not make any eventually in higher iteration, that doesn't make sense anymore. Okay, it doesn't change anymore. So when you say it's biased to zero, for example, how Robin has stated it, this is not true. If you say it, tell me that in the exam, I will come over to your house and punch you. Okay, since we assume that we sample our gradients from a distribution, okay, Agatha says, since we assume that we sample our gradients from a distribution, and if we start in zero, but we don't start in the zero, V and M start in the zero, and we give higher probability value towards zero position. Or zero position or the starting position, I would really rather that, because zero means that we are at some zero. What is zero? Okay. The bias correction normalizes scale the magnitude of accumulated gradients for early steps. Yes, and allows more meaningful steps at the beginning. And remember, guys, if you don't do this, it doesn't matter much. It helps to do it a bit faster. You could do Adam without it, and it will be just fine. You just do what, maybe two more epochs, which could be costly sometimes, but 3, 4 epochs, you know. But it's not like 2 more days of training, which is a very sad occasion if it happens. Okay, any more questions about that? And I hope it was clear what we mean by zero, the initialization of them. Eric is asking, beta is learnable or fixed? Who wants to answer? Yes, it's fixed because it's hyperparameter. Thank you, Agatha. Okay. Yes, it's there for, remember that the numbers really don't matter for you guys. Okay. So we were talking about the Newton method. Okay, the Newton method, I would like just to jump over, so I would just say that we try to approximate the Hessian. Why we try to, okay, and this is important. Why do we approximate the Hessian? If we go together to Newton method. Okay, and what do we see here? Okay, so what basically Newton method says, I really like this one. Let's go to this image here. I hope you can all see that. Let's just because I know my screen is a bit problematic. Okay, basically what it means, let's take the value of the function, okay, and divide it by the gradient of the slope of the tangent. It could be space, it could be just this linear thing, and it will take us to, or at least much closer to where the function is like the derivatives is equals to 0. Okay, it will take us to another derivative where the function hits the 0. Okay, how does it? Why do we care? So let's say the function is our derivative, is our gradient. Okay. And so if we want, and are we trying to minimize the gradient? We want our gradient function or our derivative function to go to meet the 0, right? That's what we want to do. When does it meet the 0? That its y is going to be 0, the derivative function. So we basically take the derivative of the derivative, okay? And the derivative of the derivative is the second derivative. In matrix notation, it's the Hessian. And this is the Gauss, the Newton method. Okay, great. Any questions about that? Not always, but no, it's not. Agatha is asking if it was possible to approximate a loss function perfectly with two-order Taylor, would it reach minimum in one step? I think that I've tried it before, and it not always working in one step, but it's in many, like I think maybe for such a function with one variable, it might. I don't know what to say for sure, but what I can tell you for sure that it is much faster than to do it the iterative thing that we do, then gradient descent optimizes, or stochastic gradient descent optimizes. What is the problem though with the Taylor? Why don't the Gauss-Newton method, why is it never used? Thank you very much. Leonardo has said, the correct answer, costly to compute the inverse Hessian. Isaac as a Newton, you should know, huh? But memory limitation, that's true, but you need to be more precise. Computing the inverse of the Hessian is too expensive. That's also correct. Doesn't work with for mini batches. Okay, but what does it imply, Manuel? Faster in terms of step conversions only. Also, okay, Leonardo, that's an addition to what you said. Doesn't perform well on mini batches, but what does it imply? Okay, so it doesn't. So well, we don't compute it on mini batches. Okay, we can if we do, but it's too for deep learning. Okay, so but that's a big saying to say. It implies we cannot use it for deep learning. What I want you just to say, what in mini batches it means, just if we need to, it's really hard to compute. okay, because we have to do it with the entire data set. And therefore, Manuel has said it implies that it cannot be used for deep learning. Yes, true, but because deep learning, we solve problems in deep learning that are huge and really not convex, okay? It means that if you try to do it with the entire data set, really hard to do, okay? It's infeasible to do. So this is why we don't use it in deep learning, but you need to understand why. We usually use more of the variants, the level. So I think Nisna, Professor Nisna, if he could marry this formula, he would. But because in the 3D reconstruction, he is just talking about it for like 3 different classes, lectures. He's just saying this one, this one, this one, this one, this one. We love this one. We love this one. We love this one. But it's not relevant for us. Okay, it just it is important for you is to understand why we don't use that, or if we want you to actually compute something, you need to understand what to compute. Like usually, for example, we saw it in one of the exams. We had a question. I think it was last exam. We had a question to derive or to calculate the Gauss-Newton method, and we did it for one parameter. So it wasn't the Hessian; it was the second derivatives. Okay. So the Hessian is the second derivative. That's what we want to understand here. More than that, we don't really use that here, so you don't really need to. Okay. For other classes, it's very good to know them. Okay, can we move on to training? Or let's see what else we said. This one, I don't care. Training scheduler. Okay, this is what we said. Learning rate K. Where did we see this question? We saw it in one of the exams. We'll get that. I don't want to talk about that. Okay, but splits. Let's talk about splits. Okay. So what is the advantage? I want you to give me one advantage and one disadvantage of using this split. Oh, I need to drink something. Cool. Am I stuck? Oh. So I'm just waiting for some people to answer. Oh, great exam questions. No one knows how to answer. Yes, I mean 60, 20, 20. Okay, Roy, can you please elaborate on what you said?
Maybe if data is too small, so we use like 40% of the data just for validation and for tests. So maybe it would be smarter to decrease the amount of test and validation so you can have more trained data.
That's a solution for something. Okay, but what I want us to understand, what is that? I want you to give me more full of an answer of what is the disadvantage of having a smaller training set, basically.
For a smaller training set?
Yeah, for example, we could use 80, 10, 10, but okay, what is the disadvantage of using 60, 20, 20?
All right, I need to think about how to pronounce it.
Okay, there are a lot of answers, so let me just go through them. We have quite a few data of validation and test. We have the estimated transition data. We have small training set. Okay, yes. Okay, smaller data set means small, just worse generalization. We are more prone to overfit. Okay, remember that the bigger the training set is, the more we have to generalize. We would love to have like the biggest training set that we could, you know. But the advantage of having such big validation and test is smaller training set could be overfitted, less generalization. Manuel, that's the direction, yeah, less generalization. So what is the advantage for the validation and test? Omar, that's not completely true. Oh, very good, Agatha. Yes, we have a better estimation of the generalization. A smaller data set, a smaller validation set, yeah, would mean that it could be, if we take a small validation set, it means that it's more likely to be not representative of the distribution, and then not to tell us if you overfit or not. Yes. So those of you who understand that validation set is important for a sanity check, for estimation of our generalization, these are good answers. Okay. Now I would like to hold on what Omar has written. Omar said val set is for fine tuning. Fine tuning what first? I know we do cross validation. Okay, so we fine tuning of the split. Okay. Oh, there are more answers, but I'll finish first. There was a question on CampusWire a long time ago that people said, okay, let's we did what Omar said. We used the validation set to find the best split, right? And why not to just merge it into the train set, and then we have a bigger data set to train on? What's like why not to do that? Question. And if someone can give me an answer, I would like. Well, it depends. Isaac said, okay, if you. Okay, Isaac, that's a smart answer, and that's true. In given small data sets, this is very problematic, by the way. Like when we've seen architectures that solve the problem. Yes, okay, Endin has it, is right. We need to observe the general, for my question, why do we need validation? We need to observe generalization gap during training in order to not to tune hyperparameters. We've already done that. Not to tune, we've already done that. But if we let's say, okay, I drop the validation set, okay, and then I have a train, and look at this. This is beautiful, and we already picked the best split, right? Can this tell me anything about what's going on? If we use val set on training set, we can't update the network parameters. Mehmet, I don't really understand. Okay, let me answer. Katerina asked, in lectures, it was mentioned that we can use cross-validation for tuning hyperparameters. Can we use normal val set with no cross-validation on hyperparameters? So, okay, that's a good question. Katerina, I will rephrase it again, just for everyone that will see it later. We used the validation set for hyperparameters tuning, okay? And then we used it also to find the split. I want to emphasize that these are two different steps. Okay, during hyperparameter tuning, if you guys remember for quest exercise 6, we took a split of like a fraction of the training set, a fraction of the validation set, and we use that for finding better hyperparameters, so which will be faster. And then once we've set all the hyperparameters, we want to have the best split because it's not the same thing. And then we do cross-validation with but for a few epochs to see what generalizes better. Like if you train with all of them, you will train forever. Okay, you could just, if you have the time, do it. But basically, this is if you try to do it in the same step, both hyperparameter tuning and split at the same time, what we call in Hebrew ala babala. It means kind of mess. You're making just a huge mess out of the thing. You're not really sure to find anything that's good for you, not in a reasonable time. So you can of course use you can just pick a split, whatever you want, and if it's big enough, if the validation is big enough, you could assume that it's more representative of the data distribution, which is fine. We make a balagan. Yes. So hyperparameter tuning to do it. So hyperparameter tuning, you do it a fraction of the data, then you will take all the data. Yes, Carmen, yes. So the question was, for hyperparameter tuning, I use a fraction of the data. Yes, as we did in the exercise. And for cross-validation, to find the best split, we use the entire thing. Okay, we really good, very good questions here today. I gotta say, that's a very good session that we do. What I would like to hold here. I'm fitting over. Underfitting, overfitting. Okay, guys, what does that mean? I don't want to see the answer. What do we see here? This is train, this is validation. So okay, so let's think about. So Agatha said two easy validation set. Yes, it's not. It means it's not representative of the original data set. Okay, or the entire thing, or it's really easy. For example, if we have images of cats and you just have cats, and in the training set you basically have cats under blankets or on trees, like very small. So this is much harder to learn, and it's still a cat. So stuff like that. It happens usually when we don't do cross-validation, or we take a split where the validation set is too small. Okay, that we've just said. I don't want to ask that again. I want to discuss who said that different distribution for a validation on the. Okay, so different distribution. Now let's say we trained on specific distribution, and then we give a validation set from another distribution. What do we expect to see? This, or it to be here? A balagan happened. See, you people follow on what I say on campuswire. Nice. I would also expect to see high validation because it does not know what to do with it. Right? Like different distribution means that it never saw it before. It doesn't know what to do with it. Like I would not really. Yeah, okay, but Eric, when you say mismatch, what do you mean? When you say no, what do you mean? Maybe it's too inappropriate for here. I don't know if I'm waiting for an answer or not. But in the meantime, let's continue. Okay, so we saw that. We saw these things. Right, guys, do you remember this one? You need to know how to derive. Yeah. If you guys remember this thing, it's for numerical stability of Of course, entropy, I will not stay on this right now. There are more important things to do. Hinge loss, we haven't used that much in this lecture, but can you guys tell me what's the problem? And basically in hinge loss, this one is actually a hyperparameter. It could be set, it's a threshold, and it could set to be a different value. Can you tell me what's the problem with the hinge loss? This is the most. Very good, Paul. Yes, so hinge loss saturates. Do you guys understand that? If you have any question about it, please ask. Yes, all the answers that I see are very good. Very good, guys. Okay, good. So basically, this one, yeah, is a threshold, and when we have when this is too big, when this difference is too big, yeah, then we'll have a zero, and then we'll saturate. When this thing becomes or like lower than -1, this one, the entire loss becomes a zero, and we don't need to train anymore, because that's it. We got to a point where these ones are too distinct from each other. What a hinge does, it takes the ground truth and it takes a loss that is not the ground truth, and it wants to push them away. We use that in many applications in advanced deep learning, which are quite interesting for those of you who will continue. We basically try to push them away. Let's see what people say. So we can say stops learning. Yeah, Carmen, if you say stops learning in the exam, that's a bit too vague. I would rather you to say, or either to explain what you mean, okay, or to say it saturates, and then it would stop learning. Threshold 1 here, K, yes, can be a different value. It could actually be a learnable parameter. But we're not going into it right now. How would we derive this? Vanishing and saturation gradients in the same. Vanishing and saturation gradients. Yeah, because gradients cannot saturate to anything else. So I guess. But basically, vanishing gradient. So the question of Muhammad was, are vanishing and saturation gradients are the same thing? Yeah, the same thing. And basically, vanishing gradient happens when we saturate, right? In sigmoid and tan H, when we go to the saturation areas, then the gradients are zero, so they're vanishing. That's the difference. Okay. I would like activation functions. Okay, they're quite trivial. Let's see if I have anything interesting to ask you about that. Like I could ask you, give me, like what are the disadvantages of ReLU, or what are the disadvantages of sigmoid, or what is, yeah, okay, and okay, Agatha, you said dead ReLUs. What does it mean, dead ReLUs? Which it's accepted as an answer because we use this term all the time, but what does it mean? You really want to open that? Okay. Okay, Leonardo, be careful what we say. Leonardo has said, half of the neurons die. Who says half? Who said half will go to, because okay, maybe because if we initialize the weights to be in mean zero, right, then half of them are going to be negative, and if in the input is just up, if the input is only positive, then half of them will be negative, and then zero. But that's I wouldn't go there. The gradients are near zero, so when propagating, they will become smaller and smaller until they die. Remember that gradients, is just a sec, Agatha. Gradients that or the gradients of ReLU for all numbers that are negative or equals to zero is zero. It's not close to zero, it's zero. And for all others, it's one. Agatha, you had a question.
Yes, because we said in the lecture that one solution to the dead ReLU is to initialize the biases in the ReLU neurons with a slightly positive value. And I never understood how it stops. I get it that it won't become zero in the first iteration, but it can still become zero in the subsequent iterations. And I've read somewhere that it only helps in the first iteration, and if they die in further iteration, then it's fine because sometimes they should die. Or do I understand it wrong?
Oh, well, all things should die at some point, right? I think the best solution is would use the K-mean initialization. That was proven to show that it prevents from to at least to lose the magnitude of nerves. Like with ReLU, some are going to die, but that's the part of the nonlinear thing that it introduces.
So initializing the biases does not stop it. It just makes it less probable, I guess, or
I guess so, yeah.
Okay.
And also a great solution to the dead ReLU. Who can give me something that solves it?
Leaky ReLU?
Leaky ReLU, very nice. Yes, thank you. Eric asks, Xavier is same as well, but with var2. Okay, so Eric, you're right, but we don't call it the Xavier initialization for ReLU. We call it the K-mean initialization, which is exactly the same, just is multiplied by 2. By the way, another thing that is important about the Xavier initialization, I don't know if it is Xavier, Javier, I have no idea. But yeah, Professor Xavier. Anyway, does it guide us how to sample the weights or the range of the weights? So what the Xavier initialization, what does it determine for us? How we sample the weights or the range of the weights? When we go to a distribution, right, and we take weights from that, like we initialize them somehow. Anyone have any idea? Does it, okay, range of weights, variance, right? Yes. Okay, but that's the thing. That's what Agatha says. That's what I wanted to avoid, because the Xavier initialization is just the range. Okay, it's just the variance of the weights, and it does not imply how we sample. We could do it with a uniform distribution, or we could do it with a Gaussian. But that's the thing. It's not only normal distribution. It's just a range of the numbers. There is nothing else that I want to ask about that. That's just, I guess, everything, it's just quite trivial, right? I know that I am the instructor, and for me, things are trivial, and for you, it might be not. But if you guys have any questions about any optimizers, any interesting questions about that, you go ahead and ask. Yeah, Angel, they are right. But what I wanted to point out is what Agatha said, that she said we sample from a normal distribution, and that's what I wanted to make sure that you guys understand, that you could also do it with uniform distribution from the same range with the same variance, right? No, Agatha, no, not at all. You out of all people, if you might say, you actually put it to what I was aiming for. So don't embarrass me in front of all these people. That's a good question. I believe they could change because other weights do get there. The weights change from weights do change from many aspects. It's not just one thing that flows to them. So I bet it could change. But I don't want to say it because I don't really know. We could write a PyTorch code that's really simple one to try it out. That's it's a big question for now. Okay. Okay, we just did this. Do you guys know to do it by heart? I hope so, because you should. Why, and to understand why this transition is correct, why these are 0. Like I guess some of you have already seen the question that was about the Xavier initialization, but of of minus alpha to alpha, and then you have to find like what n is equal to, and or what the variance is equal to. What a nice question it was, right? So you saw it in one of the exams. Once you guys, of course, we're going to solve all the exams, so you're going to see it. For that, Isaac, we will either we do it after we finish here, like we finish the go over the material. It's not a lot. It's not a lot. There's not much left, and then we'll solve exam questions together. So we could do it there, or yeah. Okay, let's continue. Let's continue. Data augmentation. Data augmentation is a crucial thing. Please, Guy, I want to. What is the keyword that is most important for data augmentation? I want everyone together. What is data augmentation? Thank you very much. Regularization. And why? Because we enlarge the data set. Thank you very much. Thank you very much. Yes. Okay. Regularization. So data augmentation, it has to follow the rules of following the same distribution, right? For the MNIST, right? We had the MNIST data set. It's whole handwritten digits. And what data regularization technique or data augmentation technique can we not apply on MNIST? Yes. Thank you very much. So flipping and rotation, for example, by 90 degrees, irrelevant. Another question, how does data augmentation change the size of the training set? A small rotation would pass. I'm talking about the size. There. Ops could also be problematic.
Quick question, if I may. Someone just talked about a small rotation. Like there was one exam question. Actually, it was the last one, the very last one, and I really didn't understand why a 10-degree rotation would be useful. Could you elaborate on that?
Because it does not really change the distribution. Like you could see, remember the MNIST? They have like the image, the digits also written with a little rotations, like they're little angles. They're not completely straight. So that could be okay because we have samples that belong to that. And I mean, the question you should ask yourself, will you see something similar in the validation set? If not, this is a bad thing to do. Okay, Florian is asking, why is data augmentation regularization? Regularization makes training harder, but data augmentation does not necessarily make it harder. It increases the number of learning or training samples that we see. Therefore, the network has to generalize better for the training data makes it harder. Definitely makes it harder. My question for earlier was, how does it change the size of the training set? So I want to, okay, before I want to answer my questions, Katerina asked, so we apply data augmentation only on training set, right? Not to val and test set. That's correct. And then we cannot apply flip because such samples won't be seen in validation tests. The problem is that we're going to generalize. Because what like the network would have loved to do is to overfit on the training set. Because why not? It's going to take it to 0, right? That's what it wants to do. And now you give it more samples, so it has to generalize better. The training set error will go up because it's harder for it to train. And it's not a question. I just want to elaborate on that. It means it's gonna be a bit weaker on all other things that it's seen. Like the performance of everything is gonna be worsened. So if there are no such samples in the validation, in the real world data that we want to actually train the network for, we're actually making the network worse, okay? Okay, that's why it's important to understand that. We don't want to do that augmentation. We think that that do not belong to the validation and test. Now, random question. For that, I would like to answer the question. Okay, so remember, that augmentation does not increase the size of the training set. It's physically. It does it virtually. Okay. So, and what does it do for the test set? We just answered that, but how does it affect the test set? It does not, and it does not, as Eric said, never touch, it does not, and we don't apply data augmentation to neither the val nor the test because, and if I ask you that in the exam, you answer that like that, because the test set represents real world data. And we do not, like the network needs to be able to accept unseen data that from the world. Like this is not how you answer the exam, but anyway, you do not change the test set. You do not touch the. That's it. Okay, can you repeat what happened to the training set? So the training set, we do not really change the size of it, but we do increase the number of learning rate. The training set does not change in size, but we do increase the number of training samples that the network sees. Okay. And the question, yes, team, for you, yes, it is recorded, and I will upload it when we are over. If you add more data, you add more data. That's perfect. Okay, about data augmentation, I think that we can move on because nothing more to discuss here. Early stopping. Does early stopping is early stopping considered as a regularization term? Eric, yes. So is early stopping the mechanism? Okay, so that's I like this question. Yes. Okay. Nice. Nice. I like how you guys don't have the right answer. I found online that random rotations after 20 are not useful to mention because it is already. Okay. So the answer is no. It's not a regularization term. Does it make it harder? Does it? Will it make the validation loss go? Will it make the generalization gap smaller as we continue training? No, it will just stop when the validation loss starts diverging. And this is not considered regularization. It does not make any better generalization. It will generalize as best as it can before it starts overfitting. Early stopping. Can we? Where did I see it? Go to overfitting. Boom. Early stopping is this. Okay, when this begins to happen, and we begin to. Okay, so it's just a mechanism. Right, it's not a regularization term. For the question of Manu, no, Agatha, it's not a regularization term. It's not a mechanism of regularization. It's yes, it prevents overfitting, not because how regularization works. But the question of Manuel, do we need to remember the data sets by heart? No. If there are going to be any data sets represented to you, we will describe them again as it's like the first time you've seen them. Because it's like memorizing AlexNet, right? Like, why do someone needs to memorize that? You can Google it in 2 seconds. But to understand in AlexNet, like the concept of the architecture, that we have convolutions and we have fully connected layers, or why was it bad to use big kernels, for example? Why did we switch to small ones? Yes, there was a question, how many parameters are in AlexNet, which is 60 million, but it's irrelevant. I don't find, like, did they run out of questions to ask? So, Carmen, for your question, the question was, do you need to memorize all the advanced architectures that we saw? No, but you do need to understand the concept that they represent. For example, inception layer, need to know. Res block, need to know. To see, like, for you to tell me how many layers was in the first convolution layer of AlexNet, who cares? Yes, but to know, to understand, because of course you can Google the derivatives and formulas, but you need to understand how they work. Like, before you could look at it and to not understand what they represent. You need to know how to implement that. You need to, when you see that, to immediately understand what's going on and why things work like that. For example, people still ask, no shaming intended, about the sigmoid derivatives and why do we do what we do when we implement such stuff, which is important to understand. So this is why. And if for example, we want to build something on top of that, which we could, you should know how to do that. To tell you that, just for the sake of you writing derivatives, it's not my taste, but I'm not the one to decide. I might. So, so what would memorize about AlexNet? It's not to memorize, it's to understand. AlexNet, let's go there, shall we? Okay, here. AlexNet, for example, did you see? AlexNet uses convolution of 11 and 11 and stride 4 and blah, blah, blah. And then in VGG, they decreased it to 3 on 3 and understood that it works much better than this thing. Okay, this is why VGG won AlexNet. And for example, the architecture and anecdotes of using fully connected layers for classification, because it takes the receptive field of the entire image from this feature map here, and then we can do the classification. But this one is considered the feature extractor, and this one is a classifier. Okay, things like that, like we did in exercise 10 when we took an already pre-trained architecture, right? And then we took dot features in PyTorch because this is the part, and then we plugged in a classifier. Let me ask you that. If we take a kernel with the size of the entire feature map, the entire image, spatial image, 20th, why is it that is something we want to avoid? It's a question, actually. It's an exam question. What is the difference between convolutions and fully connected layers? Ah, fuck, I answered. Okay, but yeah, it's more weights. Yes, it's less no, it's not actually less. A bit less, at least less. Bit less computations though. I think someone raised the hand. And I'm in the middle of everything. So if you didn't have any questions, you'll just don't ask. But if you did, please. Okay. The question is, what is the difference between convolutional layers and fully connected layers? In the meantime, Pam, or I hope I pronounce it right, you should tell what I hate these terms, bias and variance for overfitting and underfitting, but you guys like it. So, so basically, but you need to say that, like, I think low bias is underfitting and with high variance, and the other way around is overfitting, low bias overfitting. Sorry, I always mix them up. So you need to tell, like, what about the bias and the interesting. Okay, interesting answers. So what we have so far, we have CNN, our application of filter of function or so, weight sharing and structure preserving. The question again was, what's the difference between convolutions and fully connected layers? Weight sharing is structure preserving. With convolutions, we share weights. Also with fully connected layers. Totally two different things. No, input size can be changed. Only in fully connected convolutional layers. If you tell me that AlexNet can or VGGNet can take different inputs, you are wrong, because they have fully connected layers. Fully connected multiply all the pixels while convolutions go over. Okay, what I was aiming for is that you tell me that fully connected layers take global features because it takes the entire image and processes immediately together, while convolutions can take local features. So it could actually detect like small features. Each filter could detect different features. For example, edges, in different rotations and stuff like that. Okay, that's the big difference between them. But we can definitely represent a fully connected layer with convolution. We can just take a convolution with the same size of the spatial size of the input, which is exactly the same thing. But what we do in fully connected layers, we take this thing and we flatten it to a vector, and then we multiply it by some weights, which each of weight, like a column in a weight vector, is like a kernel. Understood. I hope so. So we actually said a lot of good stuff here today in this thing, but that's what I want you to understand. That, for example, these architectures cannot take different sizes, cannot do that. 11 on 11, this is too big. You know, it's like for 1 pixel, it's too apparently it's just too big of a neighborhood. But inception layer that we saw in GoogleNet, where did we see that? Here, it says, I am not the one to decide that. Let's just take everything. Let's take 1s, let's take 3, let's take 5, but not too big. So convolution of an image size? Yes, definitely. So the convolution of an image size, like the entire spatial size of the image, is definitely because we take a kernel, right? And we multiply all the values inside the image. If we go back to the image picture, we take them all, multiply each one of them by weight, and then sum them together. This is exactly what a fully connected layer does. Let's see, anything. Okay, I wanted, so basically this, about them, you don't need to do it. We didn't, there is a long way before we get there. Okay, we were here. I want to talk about back-end and ensemble methods, but basically I would like to talk about dropout, which is the most important thing. Okay, dropout. Dropout is a very debatable topic. And as we saw in CampusWire, there are so many different definitions of dropout. And even we saw in practice, the paper presented the probability of dropout as the keeping probability, meaning if p is 0.3, 30% of the weights are going to be saved, and all the rest is going to be set to 0, while PyTorch does the exact opposite thing. Go to, if you, Manuel, for your question on CampusWire, you just go to Moodle and you can just, there is, I think they've just shared the link there. You just click it and join the class. Like everyone can join. But you need to have you need to use, remember that, you need to use, no, if you click the link, you can use any email. If you, because we sent you emails in the beginning and then you had to use only the email that you got the link to. Anyway, dropout. Okay, so that's important. When do we use dropout? Because I saw so many of you doing the exercise and just using dropout. When do we use dropout? Thank you very much. Overfitting to reduce the coadaptation between. Yes, that's what it does. But when do I was to use that? When we overfit. We don't use that when we don't overfit. Okay, when we have a lot of layers of parameters, okay, that means the capacity is really big. That's not necessarily okay. That means that we could actually have a lot of redundant variables, and it's easy to overfit. Then we use dropout to counter the overfitting, but just as another case of overfitting. So you guys say a lot of right stuff, like correct stuff. But my question was, if I ask you, why do we use dropout? You say because it's a regularization term and we use it to reduce overfitting. And what it basically does, it just mimics those two bagging and ensembles. And when we can think of it at every iteration, it's like a different network that overfits on different like it overfits on the data set that it sees, but then we can combine them and take the mean between them, and then the results will be better. But these two are not feasible to actually implement, especially not for real world applications, because there's just too much to. So this is dropout, actually very, very good. It just really mixes all of them and adds on top of them what you just said. For example, they reduce the interdependence, or they reduce the same thing, the co-adaptation between neurons. What it basically does, if we reduce the reduce amount of neurons, 1 minus p or p, depends on the definition. It means that the neurons would have, in order to continue minimize the loss, the neurons would have to learn to compensate for all the neurons that died or were removed. So they will have to learn more things. They will have to change in a matter that will make the network learn better features. And that's the point of dropout. Roy says, when we want to make the current net to learn specific features, again, what you say, what do you mean? You mean, okay, I see, I want the network to learn to see eyebrows. So I use dropout for that? You have to be more.
No, definitely no. Yeah, you're right.
You have to be more precise about what you say. Yes, but this is why we're doing what we're doing now in the chat. So you guys practice how to answer the questions. Okay. Okay, so the testing part. Okay, so we saw two different variations. So first of all, we had two different definitions of dropout. Either it's with the keeping probability or dropping probability, and this is important. And then we have two different variations of dropout, which is dropout and inverse dropout. And inverse dropout was meant, so basically during dropout, the problem is that during training, the output, which is the input to the next layer, gets some magnitude of values. And suddenly during dropout, we don't drop anything anymore. So the problem is that now it does not, the weights of the next layer do not know how to deal with this magnitude of values. It was not trained to deal with that. So basically we need to mitigate this problem, and we try to normalize by the by key. Now it depends. If the keeping probability during testing time, we multiply by p. If it's dropping probability, we multiply by -1 minus p. And what I want to say, okay, so for inverse, the inverse dropout, you did, I don't think you really discussed it in the lecture, but you did see that in the exercises in one of the optional notebooks. Thank you guys in the chat. Okay, so inverse dropout was invented because these researchers said, okay, I don't want to imply any more calculations more than I need in the inference time during testing, because we need to take the model, the train model, and put it in the car, and I want the reaction time to be as fast as possible. So I want to avoid any more redundant calculations. For example, during testing, to multiply the numbers by some key. Okay, so what they did, basically we multiply it already during testing. I think it's here, it's one to divide by it. Let's see if I have it. Inverse dropout. We do not discuss it here. Another thing that we need to add to the lecture notes. Okay, we're not here yet. We're not here yet. We're not here yet. Okay. So let's go immediately to convolutions. Okay, because we're already 2.5 hours in, and I want to do also some exam questions. I know a long time. Okay, a convolution is application. Convolutions. What we need to know when we talk about convolutions is all what we discussed already. Okay, about the input size and the local features against global features, much less parameters. Okay, but we need to understand, for example, we haven't even discussed it yet, huh? Batch normalization and dropout for convolutions, which is different, the spatial ones, spatial. Huh? I'm not going to explain again what convolutions are, because I guess most of us know, and if you have specific questions, either ask them on campuswire. What we need to know is this. This is really important. I know we saw the question from the exam where all the answers was true. It's very good because it means that you guys know how to use these formulas. You need to understand, for example, how can I keep the spatial size of my input? Convolutions don't necessarily need to decrease the spatial size of the feature map. We can keep it. How? Question. One by one, or using padding and stride. Are the optional exercises exam relevant? Yes, definitely. For example, inverse dropout. So basically, one of them is not like to see the derivatives of, or to do, exactly. You could actually, you have, and it wasn't relevant for the bonus, but it is relevant for the material. So basically, you had one exercise when we had to deal with spatial batch normalization, and to understand how to reduce the how does the new feature map looks like, and how does the parameters of batch normalization look like, and how many parameters do we have, and it's different between fully connected and convolutions. And we'll get there, I guess, today at some point. That could be nice, actually. Yeah, I guess everyone needs a break, right? So let's get back to let's do. For me, I said that I would go with you today until the infinity and beyond. So as long as you guys have questions that you have power to continue, we will continue, because it's the only session like that I'm going to do. And so for me, I could also take now 20 minutes break, 15, 20 minutes break, and then continue. Depends about you guys. So what do you say? Let me just stop the recording. Okay, so now it's 7:26. Let's be back here in 7:45. Recording. Okay, so where were we? Yes, of course, I need to share my screen. It's working otherwise. Okay, so we were discussing some convolution layers. And while doing so, we were discussing the difference between convolutional. By the way, for the question that was above, that we talked about, if early stopping is considered as regularization, if you saw in the lecture that it is considered as a regularization term, I am not the one to say no to that, and it will be accepted. Okay. Okay, let's go to where I want to do pooling. That's good. That's good. So we saw one question that asked if pooling introduces some non-linearity into the middle. Now, this is true, but it does not neglect the need for any activation function, because the purposes are different between the two. So max pooling, for example, usually, and it's really important because in many exams we missed it. Like it wasn't my fault, but that the kernel size is 2, the default kernel size is 2, and the stride is 2. If we say something else, so we need to say that. Otherwise, if we just say max pooling, you assume that kernel size 2, because this is what the one is used, like unless in very rare cases we do something else. Okay, what's the point of that? We call that, I'll discuss that. Okay, so what do I want to say? Okay, we call that feature selection, because we go with max pooling over some feature map, and we select the most activated features. Convolutions in general, we say features extractor, right? Because it goes onto the image and it extracts different features from the image and then puts it in of course, in different feature maps that are stacked on top of each other. And then in the next convolution layers, they will be calculated together. And then the next convolution layer, these will be calculated together, and etc. and etc. But these ones, the pooling layers, only work on one channel, okay? While convolutions work on all the channels of the given feature map block that we have. Here, it's only one channel, and we pick only the activated ones, okay? Important. And remember that the derivative of a feature pooling of max pool, at least, is going to be 1 for the most activated one and 0 for all the others. Of course, if some share the same value, they're going to get the same derivative. So if you add 2 6 here, they're going to have the same derivative, which is 1. This is important. I just say that it added nonlinearity because it was a question and it was discussed, and because it does and it's quite vague, we will accept if this is asked. Okay. I want to discuss, sorry, but could you understand when pooling derivative changes? Okay. What max pooling? Yes, not just pooling. Not just, for example, average pooling does not, it's not the same. Average pooling gets, all of them, I think, get the same derivative. But basically max pooling, which it's like with ReLU, we took the max function on the kernel, right? So we take all those who are not the max value, will get 0, and the most activated neuron, or the highest number, basically, will get 1. Now, there was a question, I think in last semester, that we asked about if a ReLU on max pool is the same like max pool on the ReLU, which is not relevant for now, but I just want to say that max pool works also on negative values. So if we have only negative values, it will take the highest one, which could be like the one closest to 0, right? Right. Okay. The next question was, is convolution translation invariant? So that's it's a big mess, and it's for the last year. It's been on top of the head of the discussion, and I would like to say that it's 2 things about that. Okay, in general, a convolution just as a layer, a convolution layer is not translation invariant. It could be. When what it does invariant means. Okay, invariant means that if we change the input, the output doesn't change. It means that if we take the same convolution layer, but we change the input to it, we take an object of a cat on a huge meadow of grass, okay, and we just change the position of the cat. It means that the output, the activated neurons also move. Okay, it means it's not invariant to translation. Also, but it is called equivariant. I don't know how to pronounce that out loud, but basically what that means is that if the input changes, the output changes in the exact same manner, and that's true. Okay, so that the output will change in correspondence to the input. Okay, that is important. What I wanted to say, okay. But fully connected networks, okay. We said that it could be in translation invariant if with max pooling layer, if the translation is super small, so the max pools would still detect that, would detect the same activated neurons, and then the output wouldn't change. But that's a very degenerate case of the matter. So I wanted to go to one of the. Was it here? No, that was here. So convolutions. advanced layer. Here we go. Okay, next. So we said that convolution layers are not translation invariant, right? Are those networks translation invariant? Who wants to answer? If I change the input of the cat on the graph, will it, for classification, would it change the classification output? No, it will not. So you could say that those networks are translation invariant. Okay, and that's because the convolutions extract local features. So they could actually extract the same features from the different part of the image, this is why they're so powerful and beautiful things. Okay, now that we talked about that, okay, any questions about pooling? Any questions about convolutions? Because I think this is, of course, nothing is easy, but we need to filter some stuff. I think we touched the most important ideas. Yes, that was exactly the next thing. Yes, it came in so many exams before, so it could definitely also appear in this one. So you should know this one. It's quite easy to, you need to memorize it. What can you do? But usually, like as we saw in different like previous questions, that they usually ask you to do like one layer. Okay. A transpose convolution. Yeah, we can talk about it. There was actually a question about that, wasn't there? So, but what I want to say here is that we said with receptive field, just remember that the first layer, so if we go to the first layer here, the receptive field of this one is going to be the kernel size from the image. Okay, this is why we say k is greater or equal to 2, because we start counting from here. It's irrelevant to do the formula from here. So basically, the R1 is going to be 11 on 11, and the R2 is going to be 3 on 3. I mean under translation that we just move the pixels around, like we take an object in the image. I'm not saying scaling invariant. I'm saying just translation, just to move the object around. Translation, in computer vision means just move in space, not to rotate, not anything, just to move in space. So, for example, a house picture will just let's say like that. Annotate. Yes. Okay. I have very, very bad drawn this triangle. Okay, and this is the image. And let's say this moves here. I don't mean like it was translated to this, rotated to this, just translated. I mean just moved at the X and Y. All the pixels move the exact same way. Okay, this is translation. And for that, oh, perfect. And remember, it's not invariant to this because the output will be different. Brightest change, like, really depends on the kernels, isn't it? Like if they understand, like if a kernel, I think no, because the values that are going to be there in the output features, output feature maps are going to be different than what it would have been if you didn't change the brightness. So I think it's not invariant to that. Not that it matters. It doesn't mean that it will work bad in the classification problem. It's just not invariant, which is not that big of a deal. We just never discussed that, so it sounds like it's a huge thing. It's scary. So we wanted to discuss, I think, the transposed convolutions. Okay, so that, do we have any example here? Okay, just for a receptive field, before I move on, I wanted to say, so you do this, or you can do it by looking at the things, but I think this is just to make your life much harder during the exam. So just know that it's really not that difficult, and we usually just ask you after 2 layers, or 3, or What is the receptive field of a fully connected layer? All image. Thank you very much. Remember that. Okay. Remember that because it takes eventually the data from the entire image input. We always talk about the input, yeah, not anything else. Yeah, the input to the network, not layers. Okay, and we want to, so there we already transfer learning. Do we have any example here of? You want the note for this? Okay. Can I just send it in? Let's see. This is I2DL communal lecture notes. Can I just? Yeah. You could also find it both in the Telegram group and on CampusWire. But anyway. Where we are, we wanted to discuss the, but I need a, we have any example here or? No, actually. No, okay, we don't discuss it here. Maybe we discuss it at the end when we do units. We said transpose. That's it, right? Yeah, okay. For that, actually, it would be much better if I send you to. You have to remind me. There is like from the advanced deep learning lectures, there is a whole lecture about this stuff, and they really discuss and show with really good examples how it is done. So I think it would be just much better than me to just be talking over nothing. Okay, so just remind me. I'll send you the link. It's like okay, or do you want to discuss about that? You have like a concrete example that we could work with. Silence of the lamb. Okay, so I will continue and not touch that. Okay, we talked about that with LNet, AlexNet, VGGNet. And the VGGNet, it's like super used, so like super commonly used because it's really good, but it's super heavy, not relevant for you guys. Skip connections, residual blocks. This is important. Okay, skip connections. So skip connections allow us what we call the highway of radiance. Okay. Now, someone asked on Telegram group if we asked you to draw that, if it's okay just to do it with one. The residual block has usually these two, and it has also an activation layer, but it's not like, it's not what matters. What matters here is to understand how this is done and what this allows us to do with skip connections. What is the advantage of using skip connections? Who can say in the chat? Most of you were really right. It helps with the vanishing gradient problem. And why? Because what the engine said, that the derivatives now have a clear way. So basically, while, as we saw in RNNs or in very deep networks like this, the derivatives get shallower and shallower, although like the magnitude of them, the farther we go into towards the early stages of the network. Okay, so basically we could see that the deeper network layers would actually learn, while these don't really move, and which is a problem. now and that happens because they go through those networks and they are multiplied by stuff and disappear. And now when we use the residual blocks, we basically have this highway for gradients, okay, that allows us to move to not change at all and arrive at the appropriate place with the full magnitude, which allows us to train deeper networks and get better performance. Very nice, super easy to implement. What I'm doing right now, demonstrated, yes. I was talking about the back propagation, of course, yeah. Like during forward pass, it's not just another. It's like another thing to do, because you could basically forget them. Like you can basically forget this operation that we do with a plus. You could set them to 0. We could set these to 0. These res, like for example, if these are bad and they have weights, we could set them to 0, right? And then this would have continued like there was nothing here. I mean, that's what I mean. Sorry. Okay, is that okay?
No, I'm sorry. I still didn't understand why isn't it harm the network?
Because when we come here, let's say we come here and this is good enough to the network, hypothetically, okay? And then we do this and this, like it's just too many calculation, or it just harms the network in some way. Like this, if let's say if we remove that block, yeah, it would be good. It would be better for the network because maybe there are too many parameters. Okay, it overfits. Okay, so basically the network could learn to set all the weights here inside the block to 0, and these will basically just do the xl minus 1 plus 0, which is still the same thing. It will just pass on.
And the other way around, if this block is relevant, it's helping. Then if you
the network so the network, you don't do it manually. You don't set to 0 manually because you don't know. The network would learn it by itself.
Of course, but if you add the previous block, then it's not harming the performance in a way.
Adding the block, like like calculation-wise, like more calculations.
I mean, because you add more parameters to the next layer, like more things that can make noise or interrupt the nonlinear version.
I mean here.
Yeah.
But if this is forgotten, but the network knows, like, learns what it needs and what it doesn't. That's the thing about it.
Okay, but you put it right straight inside to the nonlinear layer.
There is like usually a ReLU here. That's
yeah,
true.
Yeah. So the ReLU knows how to take whatever it needs.
The ReLU takes what it takes. The thing is that that the networks learn by themselves what they need and what they don't, if we allow them to do so. Yeah, here we definitely allow them because we can forget these, and then the ReLU would have been like just the same, because this one is already after a ReLU, right? So a ReLU over on top of a ReLU is exact same thing. Exactly. Okay, so basically nothing. There is no harm. The only harm that could happen here is we add more calculations, right? We add like you say, okay, it does not harm my network, so let's just stack 1,000 blocks.
Mm-hmm.
That's but this calculation still happen. We just multiply them by 0, but the computer still needs to do that. And then for test time, that's bad because test time needs to be as fast as possible.
All right, thanks.
You're welcome. How does it work in practice, by the way? How will it be decided whether a layer is skipped or not? I hope I answered that, Manuel. Otherwise,
I think you just said that the network learns by itself what it needs, right?
Yes. For example, for the exam, this is something you guys need to know. Okay, like to know the architecture of ResNet, no. But the res block, yes. And this is like such a crucial thing. Like it's used in so many places, as we saw already in UNet, and it's super easy to implement. And the thing that we discussed here about the more parameters, would like still we need to think that we like if I ask you, okay, I know this is best for performance, like just means I stacked 1,000 blocks. Why is it bad? That's these things. That's the thing I want you to know. Okay, because you go out after I2DL and you need to understand networks or how to build a network. That's the thing. Okay. Good. If a gradient doesn't vanish in this addition block, do we double gradient calculate? Do we double? So usually the gradient doesn't really die here. It never goes really to zero, maybe really, really small. Do we double gradient? I don't really understand the English, sorry. To calculate the gradient twice, it is calculated in here. It is like the x is changed, or the derivatives come from this plus. If these ones are not completely 0, they will have some magnitude or some effect on like the downstream gradient. Like this is the upstream gradient that goes down the stream or up the stream. If the gradient doesn't die, dx, yeah. So we increase it, right? Like it changes accordingly. I don't know what if increase or decrease, because who knows it's negative or not negative. It changes. Okay. What I do want to also discuss. By the way, some of you like about this not absolutely, but transformed convolutions. If someone wants to add it to the lecture notes, that would be very good. Like a sub to this channel. But just because we need that here, and that's your job, not mine. Anyway, inception layer. Inception layer is also a structure that you guys need to know. There were a lot of questions about that, and like about one-on-one convolutions. Receptive field and do one example calculation. Yes, I can do that. So before that, let's just go quickly to this. We already have a question here. Okay, let's do it together, right? It's a very good practice for you guys also to do that. Okay, so remember, we said the first layer is the receptive field of it is of every neuron, yeah, is just the kernel size from. So I know it is 3. R1 is 3. We start from R2. That's what we said. So R2 is equal to R1 plus the multiplication of the strides. Okay, so it's going to be until k minus 1, right? Of I. So basically, this is just R1. So it's going to be just S1, and I can just delete this thing. Multiply by the kernel of what we have here. So this is also 3 by 3. It's okay. So basically, I'm doing. We said in the formula this is fk minus 1. So basically, this is 3. The stride that we had here is 1. So plus 1 multiplied by the kernel size of this one is 3 minus 1, which is 2. Together, it is 5. And what we could see here, that it corresponds to this, as we could see here, that this is the side that corresponds to this green and blue, and it's 5 over 5. So the receptive field is 5 over 5. And when we write in the exam, we expect you to write it like this. This will not be a bad thing, like you will not reduce points, but just because you need to understand that kernels are not always the same size in spatial. It's not like the height and width are not always the same. So these could be changed. This is calculated for each of the width and the height. If they are the same, we can just skip that. We don't need to do it twice because it's the same calculation. Okay. But usually it's just like we will ask questions like that about regular kernels because like to be assholes. I don't really understand what is K. K is the layer. So this is K1. This is K2. You could call it L1 if you like, and not, for example, if I do clear drawings and mouse, for example, I could do this L1. Would it be better if it was L1, and we could change it do it later? Or someone, we could do it now with access to the LaTeX code. Anyway, I hope that's okay. Okay, so we were talking about N and 1 convolutions. In this layer, GoogleNet, they wanted to say, okay, let's just not, let's try all the kernels, because we need to remember that convolutions are not scaling invariant. So basically, if we have big objects and small objects, it's different, like the way we identify them in the image. And some global features, more global, than the local features, and very, very small features. And one-on-one convolutions help us. We were talking about them a lot, and I have the feeling that from the lectures, they're not quite understood what they do. And we said that we use them to reduce the number of calculations. Remember that using them in front of 3-on-3 calculations will not give the exact same output as just 3-on-3 calculations, but close enough. And so we could use them to really so it's not the same thing, but it's close enough. But the advantage of reducing so many parameters calculation and parameters is so beneficial, it is used. Okay, but it's not the same, like using this or this is not the same thing. You won't get, it's not invariant. You don't get the same output, sorry. What was the problem with this? There's also a question, because how is it possible that it keeps the special size? Well, we use padding and maybe different strides. Like, I don't know if they actually say it here, but yeah, we use padding and stride. So pooling works also with padding and stride, usually with padding 0 and stride 2. And kernel size 2 here, something different here. You see another application. Usually it's not, but this is another application that we do. Okay. We said that one-on-one, there was a question that I think is false in one of the exams, that they said, what kind of layer that we've seen in the lecture could be represented by one-on-one convolutions? Question. Yes, and I don't agree with that, but maybe someone can enlighten me. Because basically, okay, let's say we have these are x, right? And we have x1, and we have x2, and we have x3. Now, convolutions, because we have depth here that I'm not gonna draw because it's bad, it's going only on this pixel. Or basically, it's not even x1 because it's not fully connected, right? It's just an image. So it's basically just grid. And we have for the first pixel, and we go to the depth, right? So we calculate. How do we calculate convolutions? We go to the kernel, we flatten it, and we flatten all the windows that we go onto, okay? And then we just multiply them with the kernel weights. So it's basically like fully connected layers, and this is why the derivatives of convolutions are exactly like in convolutions layers. But pay attention that this is not the entire image; it's just a small part of it. But this is why I don't understand why they said it's fully connected, because it's not like applying fully connected on this, where we flatten the entire thing here, and then apply. I don't know. Okay, unless we could, because we could use, but it's still not the same. Like if you see Okay, let's say it's like this. If we do have the X here and we flatten all the images in the batch, but it's in the batch, it's not like batch normalization. So Adam. And I don't know actually, so I don't want to answer the question because I really don't know what they meant. Okay. But there were questions in the previous example with one-on-one convolution, so it's good. I understand, and you understand that we go through the depths of all of them. Okay, like I think that's one of the most common questions now in CampusWire. This computation thing that you need to understand how to do the derivatives and what is like the BCE on some feature map, which is it's okay question because it's like you do what we did in a semantic segmentation that we finish with a feature map and then we need to do it cross. We do the MCE, yeah, cross for each one of the pixels. Okay, I'd like to speak about that for a little. So UNet is it's following autoencoders. So maybe before that we will talk about autoencoders. Now, autoencoders are one of my favorite architectures because I think it's super useful in so many applications. And it's really nice how it works, but there are quite a few questions that could be asked. So, for example, we've seen this before, yeah? Like this, so basically, what is the structure of autoencoder? We have we have a decoder, this part. Yes, we have the bottleneck or latent space, as we call it. And then we have the decoder. So encoder, latent space, and decoder. And they all have different meanings. So basically, when do we want to use this architecture? When did we use that in the exercise? Who remembers? I want answers in the chat. Okay, but you could use it on so many other things. Why do we want to use that? With case. Input reconstruction is something that happens, but why would I want to do that? Okay, endgame is already on the way, on the directions. And okay, let's say I have data set and I want to train, and I decide to do it with autoencoder. Why would I choose autoencoder for? Oh, Mohammed has it right. I say it like in German, has it right. Okay, we don't have a lot of data. And we want to get the most important features in the bottleneck. Okay, because we have less data. Or you could have a huge data set, which is better, but only part of it, a small part of it is labeled, which is more common. It's really, really common, especially with, for example, medical data sets, where no doctor would sit down and mark all the things that we need to do in an MRI. Okay. So basically, we don't have data, and we definitely don't know how to do that. So basically, we have just a small bunch of it. So how do we do that? How do we classify? Well, this is where this comes to play. And later on, it is used in many other applications, not necessarily for this case. But we saw it when we had a small data set with a small classified one. So basically, we force the fully connected part here to be data extractor, a feature extractor. And why is that? Because it pushes this through the bottleneck, yeah, and it reconstruct the image on the other side with the decoder. Now, in order to, because we push it through a bottleneck, it will have to do a feature, some kind of feature selection, right? It would have to take only the most relevant parts and push it through the bottleneck. Otherwise, it cannot use the not meaningful things. It doesn't have room for that. This is why this learns how to do so. Okay, that's the most important thing. Now, an autoencoder, as we saw it, for the fully connected case, for this case of small data set, that we saw it in the exercise, has two stages. Okay, the first stage was, as was mentioned earlier in the chat, for the reconstruction of the image. Okay. Okay. Question: what kind of problem do we have here? Regression or classification? Regression. Perfect. What kind of loss functions can I use? Okay, L1 and L2 are the correct answers. What kind of activation functions do I put before that? So all of you are wrong. I don't put any activation function. Regressions don't take any activation function. Before we do it only with classification. Okay. Yes, if I wasn't clear, sorry, that's my problem. Yes, if you said ReLU and liquid ReLU because you thought what I'm putting here, okay, that's my problem. If you said that you put ReLU on the output layer, that's wrong. Okay, because this is a regression problem, and regression could take any value. Yes, basically, if those are images, if this is an image, so it has only positive numbers, these are supposed to be only positive, but let the network figure this out for itself. Okay, because why do we have the BC in BCE and MCE, the activation functions, to put them between 0 and 1, not for anything else? It's not to introduce more nonlinearity, just to put them so we could use the log and to compare it to 1 and 0. That's it. But for a number, if this is 255, let this learn to be 125 by itself. Okay, so what type of learning this step represents? And let's see if you understand my formulation. Unsupervised learning. Very good. Yes, unsupervised learning. Okay, the next stage would be to take this decoder and throw it to the garbage, right? And we're left with a decoder and a latent space. And then we plug in a classifier. Yeah, it could be, as we saw in the lecture, it could be only one layer if you want. It doesn't really, doesn't matter. But we train it only on the label data. And therefore, it's a classification problem. Okay. And then we could, which loss functions could we have? Softmax is not a loss function. But BC, yes, this is the cross entropy. But BC and MC, and that's what I wanted to ask, which activation functions come with which one of them? That one? Which activation functions come with BC and MC? Corresponding. Softmax and sigmoid. Very good. Okay, and another question about these two. What do we expect in the output layer? Let's say this is a classification problem. This is a network for classification. Okay, what is the difference between the BCE and the MCE? How do we expect the output to look like for a single image? This is for the, I want for the BCE. To be more precise, how does the BCE output vector looks like? So 2 neurons, no, then I would use the MC. Of course it could, but the way we learned it. Value between 0 and 1, because this is softmax, this is the logistic regression. okay? We regress between 0 and 1. And then we have a threshold. Usually it's like half, and then we can classify between them, okay? Okay. So basically we have one. For regression, we don't need more, we don't need beans. We just need a continuous neuron. Remember, this is crucial. For classification, we need a bean, like a neuron for each one of the classes to get a score there. But for regression, it's a continuous value. Okay. So, and what kind of learning is the second stage of autoencoder is? Supervised. Very good. Supervised learning. Okay, now I want to ask you, we did here what we call transfer learning. Okay, now remember, I just gave you this as the preliminary thing. I said that the number of data that is labeled is really, really small. Okay, like the labeled data set is super small. Okay, what do I want to do with the weights of the encoder? Encoder. Okay, and I want not just the correct answer that was given in the chat. Why do I want to freeze? It's a harder question. Let's see who answers well. Okay, Philip, that's true, but I need better phrasing. Like if I saw your answer in the exam, I would probably give you the points, but I want better one. So the question again, why do I want to freeze the weights here when I do transfer learning to this classification problem when the data set, the labeled data set is really, really small? I want you to phrase your answer with the words, with the keyword distribution. Karim, Manuel, I'll answer later to that. Karim, the distribution, of course, they are the same data set, just one of them, some of them are labeled. But it's like a batch, okay? Think about it like think about the labeled data set just like a batch, a small batch. What's the problem with a small batch? Freeze them since the model quickly adapts to weights because it will optimize to the first part and not to the new part much. Who tries again? No, like what? It's a small data set in comparison to the big data set, which is not labeled. What is the problem? Oh, Philip has the first one to answer correctly. If we have a little data example, we won't able to train the large network, but it's already trained. So no, Muhammad, again, noise in the small data should not affect. Yes. Okay. So what I want to say, let's continue with that. The small data set cannot represent the distribution of the entire data set. Okay, it's not a good representative of the correct distribution. If you change the shared weights of the entire distribution that you trained on, if you change the shared weights, all according to a small batch, okay, you destroy your learning. But you're using pre-trained. You're using the pre-trained weights. I'm asking why not? Why do we have to freeze them in the decoder? And that's, I see it's a good thing that I asked. Did you guys understand that? It's like what happens to the shared weights during stochastic gradient descent. This is why a small batch size is super bad, or also for batch normalization, because a small batch size cannot represent the distribution of the entire data set. Again, small batch size or small fraction of the data set cannot represent the distribution of the whole. Yes, we update all the gradients, but we update the shared weights according to some fraction. We basically some fraction that does not represent the distribution, and that's how I want you to write it down in the exam. That's the answer I'm looking for. Understood, soldiers? Okay, again, the question was, why do I need to freeze the weights of my pre-trained encoder when I plug in a classifier and training only a small fraction of the data set which is labeled? That's the question. And the answer is that a fraction of the data set cannot represent the distribution of the entire data set. Therefore, okay, but therefore we change the shared weights, yeah, with unrepresentative gradients or something of that sort. You don't need to do it with. So, freeze them, I mean, in PyTorch, for example, we don't send them to the optimizer, right? In PyTorch, we always say, go to configure the optimizer and do model.params, send to the Adam optimizer, right? Here, you just don't do that. You don't let the network learn. It's not like you put them in the refrigerator or anything. You just don't train them. Okay, Isaac. Perfect. Okay, guys, that was I2Encoder. And I think we went over most of the important parts. Yes, I said, good. Clear drawings. Let's go back to the next I2Encoder that we know. Which is unit. Again, who wants to write my answer in the chat about the question of transfer learning? And remember, not in every transfer learning, it's the case. If you have just another batch from the same and the huge one from the same distribution, like I collected more pictures of cats into my data set of cats, it is okay to continue training the entire weights. I would just join them into the data training set and continue training. Thank you very much, Karim. Who wants to write the question? The chat was, okay, the question was, Fabian, if given the I2Encoder, right, and we try the second step of I2Encoder, we try to classify, and given that we have only a fraction of it, a fraction of the data set which is labeled, why do I want to freeze the encoder weights? Okay. Okay, so the next architecture that we're looking at is UNIT, and UNIT is a general I2Encoder that is fully convolutional. What does it mean? It means that it does not care for the input size, right? Because there are no fully convolutions, no fully connected layers here. Yes, Daniel, yes. what I want to say. Okay, so some of you guys try to do that in the network, in the homework, with putting some fully connected layers. We said that we can represent fully connected layers with convolutions, but then it needs to be, we need to understand that the kernel size, but then the input size has to be fixed, because then they have to fit the entire output. For example, here, if we have 3 on 3, of course it doesn't capture the entire image, and then it doesn't really care. So basically, you could feed any input, any image into it, and we will work, and it will output the feed. The question was here, why in the Q&A session, why is the output not the same as the input? Is because this is a general case, and it's not just for segmentation. It is usually used for segmentation, and if it is used for segmentation, the output size has to be the same as the input. Okay, this is when to try to classify every pixel. So it doesn't make any sense to not have it. Also, we use another thing here. We use skip connections. Okay, and usually it's not important for the exam. How we use that? We saw that in ResNet. We use that with the plus operation between them. And here in convolutions, it's usually done by concatenating them, putting them on top of each other, as we could see here, and then to use a convolution to process them all together, which is much better than to just add them like we did in the ResNet flow. So Fabian asks, so when I put 2 images of different size in the CNN, will the output of the same? No, like if there are different sizes, you'll get different outputs. Pause. You get if the different outputs. So if you do,
maybe I can do a little bit explanation, because on the upsampling part, I thought, and I think another tutor also said that, I'm not sure who, but that basically when we do the upsampling, then it doesn't matter what we have when we have downsampled, because we will upsample to a specific size always, and this size is always fixed. And so no matter which input we have, we upsample always back to the same size.
What I know is upsample is basically multiplies by 2. And if you use, for example, transposed convolutions, that's also not fixed at all. So it's really, I guess you could set it as a hyperparameter to the beginning, but then if in that case, the input size cannot differ. It has to be exactly the same. Or if like he said, because think of the operation that upsamples something. If you know, for example, it doesn't matter, but let's say you fix this one, the upsampling to 400 pixels spatially, but this one would give you much bigger size, or here it will even be much bigger. So I don't know, it doesn't make much sense to me, because it's not really upsampling, it will be still downsampling.
Okay, got it. Thank you.
We had some questions. Isn't it possible to define input or fully connected layer calculated according to inputs? Isn't it possible to define input for fully connected layer calculated according to the input side during runtime and achieve flexible? If you find something like that, you could basically do your thesis on it. Remember that fully connected layers have fixed W's, and they expect some size, some input size. So even if you do it with convolutions, but you expect to do it the entire image, then it has to be fixed. How does AppConf work and multiplies said? So I could share with you later on for you guys on CampusWire how this app convolution works, like the transpose convolution or upsampling works. And they have like a very nice video that shows that with examples. I think it's better than if I speak in the air about that. What else I want to talk about here? So fully convolutions to the answer to why do we use skip connections in UNet is for fine-grained features. What can I do? This was the answers from previous exams. Fun. What else? What else? Okay, we did talk about transfer learning. We could talk about recurrent neural networks if you like. No, up convolution. I don't know what up convolution is. There's transform convolutions, and there is upsampling layers, which could do it without learning. It's like bilinear interpolation and stuff like that. So it's not learned at all. It's just upsampling in a wise way. But transport convolutions actually learn. There are two ways to do upsampling: either transpose convolution or upsampling layers, which do something with bilinear interpolation or any other interpolation that you want. But they are different, okay? And one is learnable and one is definitely not, like maxpool, which is not learnable. Okay, let's talk a little bit about RNNs. So RNNs were made in order to process some consecutive data. And we, in that manner, in the very beginning, we just fed it each one of the data samples one after another, and we try to understand the relations between them. So, for example, a sentence. So we want to understand which word corresponds to which word. Problem: we do not. It doesn't manage to really capture entries or inputs that do correspond to each other, that we humans understand really well, but that they are far from each other. So, for example, something that is written in a new sentence or 10 words later, but it corresponds to something that's said in the beginning, and it does not learn it well. Why? First of all, because of this concept, because they don't see each other at the same time. Data from inputs at the beginning have to be processed through other things that multiplied it and changed and modified throughout the network until they arrive to the next corresponding word. So it's completely different. And what is the problem? The big problem, or we could say even the two big problems with RNNs. Very good, very good, very good, very good, very good, very good, very good. So with vanishing gradients and exploding gradients. And why does it happen? Another example. Yeah? So so Fabian was already going further away. Let's think about first how does this cell looks like? This is an RNN cell. Okay, remember this and this and this. What is the problem? Engin has it right. Is right, okay. Hidden states is multiplied with always the same parameters, leading high power of matrix with eigenvalues. Okay, now comes the idea of the eigenvalues. Because of long chain rule in propagation, yes, that's true, but the idea that we use the same weights. Remember that in other networks, each layer had its own weights, not connected. But here, the blocks share the same weights, and they're multiplied by each other. And then that's a problem when we do backpropagation, because if the eigenvalues of the weight matrices are not one, it's bigger than one, smaller than one, they either explode or vanish. But guys, remember, I know it's already late and we've been here for almost 4 hours. Okay, very nice, by the way. But I still want you to try and write concise answers. We are at the very end, but I want you to try to formulate what you would write to me in the exam. Okay, am I asking you this question? And I'm telling you, this is we've said it before. I need the answers you will give me to exam. If you say to me, for example, let's do some training to Herr Koenig. If you write eigenvalue is not equal to 1, that's not an answer I could take. Okay. Things we considered as an advantage that we only have so less parameters. So basically, computationally, it's or at least in the memory, it's not that bad, but it doesn't perform that well. Great question, Fabian. Okay, that is the most I want to do after RNN. As I said in the beginning of this, I do not expect you to know to do the propagation through it. So don't waste your time doing that. You have enough time, other things to do. So this is what we said, the solutions that are interesting. Also use LSTMs, right? That's also a solution to this problem. Just don't use that because LSTMs allow us the flow, like the skip connections, like the flow of the gradients. There are two answers. Either normalize the weights to have eigenvalues of 1, which is hard to do, or just don't use RNNs, use LSTMs instead. Or transformers, that's also an option. Just don't use RNN.
Could you talk about gradient clipping briefly?
Gradient clipping. Let me remember. I did it half a year ago. Why do we do, and why does it help so much? Well, you guys does everyone know? Okay, remember, gradient clipping is when basically the gradients go through some like pass some threshold, and we just cap them to this threshold. So basically, if I want them to be in the range of -5 and 5, every gradient or that its value is lower or greater than that, or it's basically not in the range, we clap it to this, and that prevents the gradient. Sorry, I'm already exhausted. The vanishing gradient or the exploding gradient. Okay, I think that we saw in advanced deep learning that it is actually really well used because it was shown that it is super good to do that. Even on top of, I don't remember what it was, but I remember that it actually replaced something. But I'll have to go back and find it, the answer. Don't want to just say stuff in the air. But did you guys touch that in the lecture here? So basically, the only thing you need to know about that, it prevents, it works pretty well, and it prevents the vanishing and exploding gradient because it's like, I don't know if it's not really like batch normalization, but we managed to keep them in the same, we cut the magnitude. So yeah, and it really helps with these problems. Okay, you need to know that it helps with a vanishing and exploding gradients problem. Right. Sorry. So you're right. Only the exploding. You're right. If they're small, it doesn't help. You're right, Philip. Sorry. Felix said it's important for the recording. How does it help with the vanishing gradients? It only helps with the exploding, and this is true. If the gradients are also very small, clipping them won't help anything. Normalizing them, however, could keep them in some magnitudes. But for that, we have the initialization of the weights that we saw that works pretty well. LSTMs, I don't want to go over here because I haven't touched them in a long while. It's just useless for me. And okay, so transformers are things that's going to appear in the exam. Like they could, they introduced this the first time here, so I assume they would like to ask about this. Also, for example, I think the Monte Carlo dropout, it was also introduced here, so something that we should go revisit at least. So I gotta tell you, I did not prepare myself to go over transformers, so I don't want to do it right now, because I will need to recap that myself to be able to teach it. Okay, so if you have any questions about that, please ask us on CampusWire, and then we will go over the material and give you a proper answers. Okay, so now let's just stop the recording.